Julius. Julius. It's been a while since I talked with you.
Hi, Phil.
Yeah. I'm sorry I haven't sent anything in. I haven't been able to use scopes or anything for about 2 years.
Well, when you get a chance, it'd always be welcome, no problem.
Yeah, well, I tried that occultation of Titan the other day, a couple of weeks ago. It was a real test, but I kind of got it, but I didn't get really accurate timings or anything.
That's quite interesting. Also, several observers have sent me some images and videos of the transit of Iapetus on Saturn. On the 18th of July.
Was that?
18th of July was when it occurred. It's a kind of a rare occurrence with the rings not being edgewise. They're tilted enough right now so that there can be transits like this, but it got quite a bit of attention.
Yeah, well, the reason I tried this because the last time Titan calls it a fifth magnitude star was in 1989.
Yeah, quite some time ago.
It was, I was working and it was pouring down rain anyway, so this will be the last time I'll get to see it. I think they said the next one is in 2049 or something like that.
Yeah, well.
I did a little write-up. If you want, I'll email it to you.
Okay, great.
You can do whatever you want. So you can toss it or whatever.
Yeah, I thank you. Great. We appreciate it.
All right.
Good to see you.
Same here. Yeah, my day's not over. After this morning session, I have to bug out and drive 30 miles to go to our club meeting. I think they're going to try to get the YouTube talk by Chuck Wood.
Great.
At 7 o'clock. Then we'll have our meeting afterwards. It's a 30-mile drive. I'm dead tired right now. So how's your son? I forget his name.
Oh, Matt. Yeah, Matt's doing great.
Yeah, we all met in Atlanta having a beer.
Hey, everybody.
I saw him again. He's out west somewhere, Ventura.
Oh yeah, sure.
And we were talking guitars.
Yeah, that was a great conference out in Ventura. That was really nice.
Yeah, I guess they went over budget.
That was fun, wasn't it?
Yeah, it really was.
It went over budget, they said.
Yeah, we did a little bit, yeah. Yeah, I coordinated that thing.
Yeah, I kept that in mind when I had to do my bit.
Yeah.
Spreadsheets were pretty handy in keeping everything in line.
I think it's the only conference we've had sponsored by Budweiser, though, too.
Oh, I still
got my hat.
I still like Walter, but the Budweiser girl sitting on his lap.
Yeah, that was pretty classic. That was a fun one.
The next year, Don Parker said we were going to have our board meeting, but our leader didn't show up because he was elsewise busy, and he showed that slide of Walter with the
right.
Oh, good memories.
Yep, it was a long time ago. 22 years.
Yeah.
It's hard to believe how fast time passes, I'll tell you.
It's crazy.
Amazing.
Yes. So someone was talking about time, time like that yesterday. I just remembered later on that I went to a IOTA Zoom meeting, the last one they had. They were talking about actually using time dilation to put it in their timings because the asteroids are so far away that there's, I don't know, some kind of a time dilation. So I wonder if that has any effect on our planetary observations too.
Yeah.
I know it takes, well, I mean, the time the occultation happens at the asteroid is different than the time we see it. Something like that. I'm not up on my relativity. Guys getting any rain out there?
We're getting plenty of rain here in Savannah off and on, just the afternoon thunderstorms and washes out good observing opportunities.
Yeah, it's probably going to be raining when I leave here.
I keep seeing all that all those storm systems coming across the Midwest.
Yeah, we're supposed to get some of that.
Where are you at, Phil?
Ohio.
Oh, okay.
Yeah. I'm up between Cleveland and Pittsburgh. So all my life I heard the arguments between both football teams.
And now you have the Guardians, huh?
Yeah. Oh, yeah. And Heinz Field is no longer Heinz Field.
That's terrible.
Yeah,
That's blasphemous.
That's kind of a weird insurance company named Askew or something like that.
Well, I think they signed a contract with Heinz for the scoreboard, so it's still the Heinz scoreboard.
Oh, okay.
So they're not going to remove the ketchup bottles.
Yeah. No, I've never been there. I've been to the ballpark.
Mm-hmm.
That's the only pro baseball game I ever went to.
Oh, wow.
It was the best night I had that summer. I was working 6 days a week. So I had my Sunday off. So a friend of mine had 4 tickets, because one of his suppliers, he was a doctor. One of his suppliers gave him 4 tickets to that game. So we went up there. We were sitting 20 seats up from first base.
Mm.
Pretty good seats. And you can see the big sign and all that. And you can see downtown Pittsburgh and over the outfield. It was cool weather. I really enjoyed it. The Pirates won in a walk-off home run.
There you go.
So I'm not a big baseball fan. But I miss sitting around with all you guys, having a beer or whatever. Anybody hear how Mike Maddie's doing? No?
Nope.
Yeah, this is Julius. I haven't heard from Maddie and Mike Maddie in a long time.
Hmm.
He used to send me Venus observations quite some time ago. I want to try to get in touch with him to see how he's doing.
Yeah, he had that program about watching volcanoes at the Terminator. You can see the cloud thing. I don't know whatever happened to that. Hey, Matt.
Hey, Phil.
How you hanging in?
Oh, okay. I'm doing fine. I hope you're doing well too. I saw you yesterday.
Yeah, I didn't talk to anybody.
Oh, you're testing
Go
your
ahead.
charts out there.
Pardon me?
That's good to see you're still alive and well there in the Youngstown area.
Oh, yeah. I was telling the guys, I got a meeting tonight at 7. I got to drive out to the observatory. It's 30-mile drive.
Yeah, I imagine you really have to get outside the city to get really decent skies.
So LEDs. They're killing me here.
Mm-hmm.
I got 2 spots with like a 3-foot square place where there's shade where I don't have light glaring in my eyes.
Yeah.
All I can do now is use binoculars and do some variable stars, and that's it. I know you guys don't like variables, but
Yeah. Well, I can still get into, I live in a suburban area here in Springfield on the west side, but I can still get out with the scope to do planetary stuff.
yeah.
On the very best nights still, and in the backyard, I can see Andromeda on the very best nights. So it isn't quite that bad, but.
Yeah.
But, the thing in suburban areas that a lot of people complain about is a light trespass issue. So.
Yeah.
That can get to be a problem if you have a neighbor that just wants to put a dusk to dawn light out or something.
Yeah, I don't understand it. Like they put lights up, and crime keeps going up. I don't see how.
Well, yeah, it's a false sense of security. Glares it. Yeah.
All the lights do is help the criminals.
Well, glare is a bad thing. It reduces visibility.
Yeah.
We got a situation here in Metro Atlanta. Are any of you familiar with the electric vehicle maker, Rivian, Rivian?
Yeah, I've heard of them.
Okay. Southeast of Atlanta in the country in Newton County. It's pretty rural. And that's just south of that is where where the Atlanta Astronomy Club has a chapter called the Charlie Elliott chapter of the Atlanta Astronomy Club, because it's named for a guy who was very much into the outdoors, and it's a nature center. They got controlled hunting and stuff like that, fishing, and that's where the chapter meets. It's extremely active. We have a dedicated observing field. We do very good there, and it's not perfect, but it's a lot darker than being in really metro Atlanta itself. It's about 40 miles outside of downtown Atlanta. Rivian is building a battery plant there, and it's gotten to be really nasty, because we know when that plant goes up, not that many miles north of the Charlie Elliott location, it's going to mess up the skies. The locals don't want it, okay? But Georgia being so pro-business, the state stepped in and totally took over the negotiations to give them every tax break they could, and locked out the county of Newton and the local municipality from any objections. And so Rivian is going to be building a giant battery manufacturing facility there. Well, anyway.
Oh, that's bad.
Okay.
That's too bad.
So I got my my ramen soup and my iced tea and my sub sandwich. So we in the Eastern time zone have lunch.
Yeah.
Great board meeting last night, Matt.
Well, thank you. I think it was too. Thanks for contributing also, Ken.
Yeah.
I thought about attending that, but after I signed out, I watched TV for about an hour and I slept till about midnight, and I was up, and I was out doing variables at 2 a.m. I was on the computer till 7. And I went to get gas and stuff like that, and I came back, ate a little bit, and I was on the computer again, and now here I am again.
You're up near Youngstown, right?
Yeah.
Yeah. I'm from Cleveland originally.
You was that you that thought I was Rick Hill, the new Don Jenkins?
I remember talking with her and meeting up with her. Yeah, she and her husband live in Lakewood, which is just east of Atlanta. I used to live in Lakewood before moving here.
Yeah.
Have you been in touch with her or anything?
No, you ever hear of Black River?
I've heard of it.
Black River?
I've
Yeah.
heard of it.
Well, last time I talked to her, I went to their meeting. That's out in I forget the name of the town. Well, anyway, it's up near the lake.
Yeah.
So I went to their annual meeting. I saw her there. I recognized her from 1990s. We talked a little bit. She used to put out the newsletter for the regional group called the OTAA.
Ohio Turnpike
Yeah,
Amateur
Yeah.
Astronomers, I think, was something like that.
Yeah. It was. Oh, geez, I can't even think of the name of it. I just bought like all the editions that the AA show had. They wanted to get rid of them, so they emailed me if I wanted them or somebody else wanted them. So I emailed all the clubs. Nobody wanted them, so I bought them. $38.
All right, we're gonna wait a couple more minutes for some more people to join us. Right now, we have 30 people on Zoom, and we have 6 people watching on YouTube. So I'll wait a little bit longer, then we'll start.
Okay.
Hi, Philip. Hi, Philip. How you doing?
Hi, Frank.
Doing good, Frank.
Yeah.
Hi,
Okay.
Frank.
Hi, everybody. Day 2, right?
We got to turn this into a 3-day event.
Supposed to be in the 90s here. It's gonna be the 90s here in Atlanta. What's it gonna be in Long Island, Frank?
What's that? I'm sorry. What
It's gonna be in
about?
the 90s here today in Atlanta. What's it gonna be up there in Long Island?
Oh, the weather-wise, it's in the 90s.
90s?
Yeah. New York City is in the mid-90s, but out on Long Island it's a little cooler because we're right by the ocean. So we got the ocean onshore winds, so that keeps the temperature down a little bit. So it's still, low 90s. No.
Yeah.
Are you, Phil? Are you still located in Ohio? Or you still,
We're
still there?
Yeah,
Okay.
I'm still here.
Yeah.
Hanging on. The usual things to worry about. I'm retired now, but
Are you doing? Okay. Yeah.
nothing
Yeah.
gets easier though.
Yeah. Well, at least I have another year to go before I can retire.
Yeah. I feel sorry for the people that are retiring right now that have to start tapping into pensions and stuff like that, and where the
Yeah.
stock market was going.
Yeah, that's what some people, they delay their retirement. The way,
Yeah.
they worry about they can't afford it, or they got to keep working until 70. But
Yeah. Yeah.
it depends on many situations. Yeah.
I told a guy last year, at the end of the year, was running my IRA, told him to get out of stocks and put everything in bonds. He said, no, okay, I got to go to the dentist. And he walked out and said, I'll figure out something. And he never did.
Yeah.
So,
But IRS is a temporary job, right?
what's that?
IRS.
IRA,
Oh, IRA. Yeah, I thought you said
Yeah, it's a-
IRS. Yeah.
individual retirement account.
Yeah, right. Yeah, IRA.
Yeah.
Yes.
Well, when I retired, I transferred on my 401k, which I never, I put maybe $1,000 in it. That's all I put in, and it was up to
Okay.
like
Yeah.
$39,000 when I retired, and I put it in the IRA, and I had it up to a little over $60,000.
All right,
So you-
Because of the stock market now.
all right, we're gonna get started now. Can everybody please mute themselves so we can do this? And I will.
Okay.
All right, Welcome to day 2 of our virtual ALPO conference. Again, my name's Tim Robertson. I'm the host of this event. Today, I'm just going to briefly go over the schedule. As you see on the screen, this is who we have speaking today. Again, we're going to be taking a break halfway through, about a 20-25 minute break halfway through. And then we end with Julius Benton talking about Venus. That'll be it for this session. And then another Zoom link will be sent out following this meeting for the keynote address, the awards, and the door prizes we have. So as we watch this, as you watch the different speakers, if you have any questions, put them in the chat. It makes it a lot easier that way. And if you're watching on YouTube, thank you very much for being over there. We have 9 people watching right now. And just put your questions in the chat also on that, and I will monitor that as we go throughout the day. Also, if you're watching on YouTube, please give us a thumbs up. And if you haven't already, please subscribe to YouTube. Really appreciate it. So this evening, like I mentioned, we're going to be having the keynote address and door prizes and our awards. We're giving away the Walter Haas Award and also the Mike Reynolds Award this evening. Some of the door prizes we have for tonight, the way you get them, you have to be a resident of the United States, because we don't want to ship across the world. That gets really expensive with the way postage is right now. But one of the first things is like from Bob's Knobs. I don't know if you can see this. A certificate, collimating thumb screws. It was very nice for that donation. From Celestron, we have a Edge 10mm flat field eyepiece. Also from Celestron, we have an Edge 18mm eyepiece. From Explore Scientific, we have an 82-degree 8.8 waterproof eyepiece. And then we have this monster here. This is an eyepiece. Good luck with this, okay? You need a counterweight. This is an 82-degree 30mm waterproof eyepiece. And Explore has also given us a 2-person tent. I'm not going to pick that up and put that in front of the camera, but they've also given us a 2-person tent. So we've got quite a nice selection of door prizes for this evening too. And the way you register is send me an email if you live in the continental United States. If you've already registered for the conference, I've already got your emails. So you don't need to do it if you've already registered. And we're just going to draw email addresses out of a hat or a bowl or something like that during the keynote address. And that's how I'll be giving those away. We have any questions before we get started with today's presentations? All right, Ken, I'm going to turn it over to you.
Thank you, Tim. Okay, our first speaker of the day had some big shoes to fill a few years ago when he succeeded Wayne Bailey as coordinator of the lunar section. David Teskey of Louisville, I guess it's pronounced Louisville, Mississippi, in the east central part of the state. He has been the coordinator of the Lunar Topographical Studies program of the lunar section for 3 years. The lunar section is structured in sort of differently from everybody else. It's just a bunch of our programs, but he is more or less regarded as the overall coordinator. As such, Dave works with lunar observations from fellow lunar observers across the world. He has been a lifelong amateur astronomer and is particularly interested in lunar and solar observations. His program for today is entitled Sailing the Sea of Clouds, Exploring Mare Nubium. And he's going to discuss various lunar features that can be seen in Mare Nubium, and using both small telescopes as well as lunar orbiting spacecraft. He's also going to discuss the Lunar Topographical Studies program and shamelessly solicit even more lunar observations. So I now turn it over to Dave Teskey. Go ahead, Dave.
Thank you. Appreciate that. 1 second. Can you see that?
Yes,
Does that work?
Yes.
Okay, great. So today we're going to be sailing the Sea of Clouds, which is Mare Nubium on the moon. And what I'm going to do is talk about a little bit why I look at the moon, a little bit how I do it. We'll look at an overview of Mare Nubium, some great features that you can see with small telescopes in Mare Nubium, and how you can do even more later on. So why I explore the moon is easy. It's our nearest neighbor in space. There's a wealth of detail visible even with the smallest of telescopes. I heard some chatter about light pollution. Even light pollution doesn't hinder our view of the moon, and it's visible most of the month. And those last two features may or may not be of benefit to some astronomers, right? How I explore the moon is with small telescopes. I use mostly a 4-inch f/15 refractor to look at and image the moon, and sometimes a 3.5-inch Maxituf. And what we're going to do is look at Mare Nubium today, just to zone in on that and use that kind of to explore the whole moon. Mare Nubium is also known as the Sea of Clouds. It's located in the southwestern section of the moon. I have it highlighted here in red. It's got an area of about 254,000 square kilometers. So that puts it between the size of the country of Romania and New Zealand. And its diameter is around 750 kilometers, though the northern boundary is pretty nebulous. So what are some features that you can see in Mare Nubium? I'm going to start off on the eastern end with a crater called Thebet. This crater Thebet, 56 kilometers across, is of Imbrian age, which puts it at 3.2 to 3.75 billion years old, give or take. And it's a neat crater to see because it's overlain by another crater, Thebet A, which is about 20 kilometers across. And that's perhaps even overlain by a smaller crater, Thebet L, which is around 10 kilometers across. As long as you're looking at the Thebet area, look more closely and you will see ancient Thebet. This is an unofficial name, but it is a crater. It has dilapidated crater walls around 200 kilometers across, and this is a buried or ghost crater. Yesterday, Tony Cook was talking about buried craters, and this is one of them. It's only visible when the light is just right, so you can see the wrinkle ridges there. It turns out ancient Thebet was formed after the Nubian Basin was formed, and later it was covered by the Mare lavas, turning ancient Thebet into a ghost. Well, as long as you're looking here, you can't help but see the straight wall, officially known as Rups Recta. And this is a fault in the crater of ancient Thebet. Its length is about 130 kilometers long. Its slope is 10 to 40 degrees, so it's fairly steep, but not a wall. Nor is it straight if you look at it closely. It rather looks like a sword at times. At the bottom, at the south end, are the Staghorn Mountains, another unofficial name that forms the handle of the sword. And the Staghorn Mountains are actually probably the remains of a couple of crater rims. The straight wall, Rups Recta, is beautiful to see anytime during illumination. You'll see it first in the morning hours, a little bit after the lunar morning, I should say. A little after first quarter moon, it will be a dark line that you will see. And in the evening, the lunar evening, you'll see it as a bright line as it's lit up by the sun. And that is around a last quarter moon. As long as you're in this region, let's look at two fascinating features, the crater Burt and Rima Burt. Burt is a fairly fresh crater. It's funnel shaped. It's about 16 kilometers across, and it is overlain by another craterlet, Burt A, which is about 6.8 kilometers across. It breaks the eastern wall of Burt. And just west of Burt, here's a little challenge for you with your telescope, is Rima Burt. It's a rill about 50 kilometers long and around 1.5 kilometers wide. And this is believed to have been an ancient lava channel. And if you look very closely, you can see the pits where the lava came out of on Rima Burt. It shows up easier in images, perhaps, than it does with the eye at the telescope. So what happened here to form Mare Nubium? Well, long ago, of course, an asteroid blew out Mare Nubium, if it is indeed a basin. That's at least a little questionable because the northern edge is pretty nebulous. There's not much to it, but that does seem to be a southern rim. Sometime thereafter, the large crater ancient Thebet was formed, and Mare Nubium was later flooded by mare lavas. These mare lavas caused the basin to sink towards the middle, was heavier, and craters like ancient Thebet and other craters sank towards the center of the basin, and the lavas flooded their outer edge walls. So several of these craters here, you notice their walls towards the center of Mare Nubium are pretty well gone. Later on, Rups Recta, that fault formed by stress forces, and later on after that, there were small craters formed like Burt, and perhaps the last events there were those lava tubes. Yesterday, Tony Cook mentioned the Lunar Reconnaissance Orbiter, and this is a wonderful tool that amateur astronomers can use. It is the Lunar Reconnaissance Orbiter is a orbiting spacecraft around the moon. It's imaged the moon a bunch, and you can actually go on its website and you can draw a line like I've done from A to B across ancient Thebet, and then it will draw out a profile of that terrain. And here you can see Rups Recta, and you can see that definitely ancient Thebet slopes to the west or to the left. There's some cool stuff you can do, by the way, with the Lunar Reconnaissance Orbiter. I was talking to Ken the other day about it. Launched back in 2009, it was our first lunar mission from the United States in more than a decade at that time. It's imaged a bunch of the moon at high resolution, and it has returned more data than all the other planetary missions combined, partially because it's so close to us and sends back so many pictures. The features like the quick map are openly accessible to all. Yesterday, Tony Cook was showing us layers that can show us features that we just can't see otherwise. This is a really cool image. If you look carefully, this is the Apollo 12 landing site. The Apollo Intrepid descent stage is still there. The Surveyor 3 spacecraft is there. You can see it. That's where the astronauts walked over and took the camera off of that robotic spacecraft. And if you look carefully, you see thin dark lines, and those are actually the paths of the astronaut footprints on the moon. So this is some of the only really hard proof that astronauts were there. I mean, you can actually see this with the orbiter. And a great challenge for you if you have a rainy day is try to find these landing sites without help. It's a challenge. They're small. Back over to Mare Nubium, you can see we just looked at ancient Thebet, and we looked at Rups Recta and the crater Burt and at the Rima. Now we're going to go to the southern shores of Mare Nubium and look at the crater Pitatus. This large crater is about 97 kilometers in diameter. It has an off-center central peak, and around the edges of its inner walls is a rill that circles this crater, crater Pityus. Next to Pityus, to the west, is the ancient crater Hesiodosus, which is around 43 kilometers in diameter. And just west of Hesiodosus is Hesiodosus A. It's a concentric crater about 14 kilometers in diameter. It's always easy to see Hesiodosus A, but to see it as a concentric crater is kind of tricky. You have to have the light just right. When it's just right, it looks kind of like a donut. We see a drawing on the lower right by Robert Hayes, a recent drawing of his, and you can see Hesiodosus A as a beautiful concentric crater. How it was formed was either a volcanic extrusion or an annular intrusion from below. It looks like a crater formed right in the middle of another one, but that just doesn't seem to make sense because these concentric craters form mostly on the edges of the Maria around the moon. Near the center of Mare Nubium is the beautiful crater Boleodus. Boleodus is about 61 kilometers across, and it's a very nice Tycho-like crater. It's one of only about 13 fresh lunar craters on the near side of the moon that's 60 kilometers in diameter or larger. And you can think of some like Copernicus and Tycho. It's in that class of crater. When you look at Boleodus, you'll see that it has terraced walls that are really nice, but not really raised like Tycho has. So Boleodus must be older than Tycho, probably Aristotelian in age, a little bit more than 1 billion years old, say. As long as you're in the area of Boleodus, look below it to the south at the crater Keys. This is one of my favorite regions of the moon. Keys itself is a flooded crater. It's about 44 kilometers in diameter, and its rim protrudes about 380 meters above the floor of Mare Nubium at the highest. And if you think of that, that's still a fairly good ways, half a mile or so. And just west of Keys is a feature called Keys Pi. This is fascinating. Keys Pi is a lunar dome, and lunar domes are caused by some sorts of volcanic activity that push up a small rounded hill. In the case of Keys Pi, this dome is about 14 kilometers across. And if you look carefully, there's a summit pit, which is large enough to see through, again, a small telescope when the terminator is nearby. Looks kind of like a shield volcano, doesn't it? The light has to be just right to see something like this. It has to be very near the terminator. Ralph Lina over in Rome is the ALPO and BAA dome coordinator. He does a lot of studies of these domes, and a dome like Keys Pi is actually a very easy one for you to see and study. Near the center of Mare Nubium is a most unusual crater. Its name is Wolf. It's around 25, it's supposed to be kilometers in diameter, though it's hard to determine a diameter here. Here, it's at least one or more crater that has coalesced together, and the remains of it, again, were flooded by Mare Nubium. And towards the northern shores of Mare Nubium is the crater Lubinenski, northwest of Boleodus. And Lubinenski is around 44 kilometers across, and its southern wall, again, is mostly missing. So much like ancient Thebet, after the Nubian Basin was formed, Lubinenski was formed by impact. As the lavas filled the basin, The crater tilted towards the basin center and it was flooded with lavas. So what do we have when we look at a basin like Mare Nubium? If we go back to the Lunar Reconnaissance Orbiter, we can draw a line from east to west across it, A to B, and we can see here, we can plot out the elevation, and generally, Mare Nubium is bowl-shaped from east to west. The bumps here and there as we go across are probably craters that the line was drawn over. Again, if we go from south to north, we again see Mare Nubium is pretty well bowl-shaped. It dips down a little bit more towards the center. So you must say as you watch this, how can I learn more about the moon? How can I contribute something about this? Because I'm pretty sure everybody here looks at the moon from time to time. It turns out ALPO has a very active lunar topographic studies section. And it collects observations from lunar observers around the world and publishes a monthly newsletter called the Lunar Observer. And we'd love you to feel free to contribute your lunar observations, articles, images, and such. You can see here from April through June that just finished up, the country, the observers per country. We see Argentina almost always leads with this. They have a whole lot of active lunar observers there. The USA does pretty good. Italy does very good. And then we have a bunch of observations from a lot of Latin America, some from France, some from the UK, and recently some from China. So it's kind of fun to get observers from all over the world and New Zealand as well. So check it out. If you haven't seen it, this is the latest edition of the Lunar Observer. You can see it's got a number of articles authored by fellow lunar observers around the world. And this latest edition was only 127 pages long. Ken will tell you some have been longer than that. That's okay. And we can again see that last month, for example, there were 116 observations contributed by 30 observers from around the world. Those observers, by the way, I keep track of their telescopes. Maxitovs and Schmidt-Cassegrains usually win. They won again last month, though reflectors and refractors were holding their own pretty good last month. Usually the largest telescopes we have are something like a 12-inch Meade or a Celestron 14, but most of the observations are made by telescopes like 8-inch Schmidt-Cassegrains are smaller. So you don't need a large telescope to join us. And we have great articles. Alberto Annunziato in Argentina, he's our assistant coordinator, and he has focus on articles every 2 months. And this is from last month's the Lunar Observer. We were focused on the wonders of the full moon, in this case, rayed craters of the northern lunar hemisphere. And we had a really nice article there. Next month, we have rayed craters of the lunar southern hemisphere. Look in your archive data, see if you have some images from Tycho and the craters in the southern hemisphere with rays, and send them in. And we're even planning for November. We have the ever-changing Eratosthenes, a beautiful crater at the base of Mare Imbrium that we want to take a look at. Does anyone have any questions or comments?
David, I'd like to, first of all, echo what a lot of other people are saying. You're doing a great job. It's a great talk. And we do have some time because you did run a little short. And I know that Julius had some other programs. There were some great, there were other programs within the lunar section that I don't know if they're active or not, but do have a few minutes if you wanted to touch on any
Yes.
of the other things.
Yes, I mentioned Raphael Lena over in Rome. He is the lunar dome coordinator, and he does very, very in-depth studies of lunar domes. You'll see his reports in the journal from time to time, and he really does in-depth analysis of the domes. So when I get images and data about domes, I send them his way. Brian Kudnick is in Houston, and he does lunar impact studies. And from time to time, we do have lunar impacts. Just be a flash of light here and there, but he studies those. I think one of the more interesting ones was during an lunar eclipse back in January of 2020, I believe it was. We had a impact during the total lunar eclipse. So he studies that. And Dr. Anthony Cook, who we had on yesterday, he does lunar geologic change, which is fascinating because in years past and today, but particularly in years past, observers would see things such as color changes in craters like Plato or gaseous, nebulous things on the moon. We don't see them that much right now, and it's like, what's going on? So a lot of what he does is he looks at timings when the lighting conditions will be the same as it was for these historical observations, and people look back and draw and image those features to see just what they were seeing. And oddly enough, there are a number of features that may well be actual transient events on the moon. And there's been a number of explanations for those. Volcanoes seems a little far-fetched, but some things like dust being elevated by electric forces at sunrise and sunset and such could be causing some of this. So it's pretty interesting.
Hey, David, we have a question on YouTube from James Fisher. How does one subscribe to the Lunar Observer?
How does one subscribe? Send me an email and you just subscribed. I'll get it to you. I'll put my email on the chats.
There was a program called Lunar Selected Areas. I don't know if it's an inactive program.
We do that as well. There's like 8 areas on the moon that ALPO concentrates on, like let's say the crater Tycho, and it's very well mapped, and the observer would note various brightnesses and shadows and mountains and such. A couple years ago, for our Focus On section with Jerry Hubble at the time, he did a lot on those selected areas.
And I'd like to also add, you don't need a computer. You want to talk about Robert Hayes and his work?
You do not need a computer to do this, though. If you're watching this, you do need a computer. But no, we get Robert Hayes has since the late 1990s mailed in his observations of the moon. I showed you one of them on my PowerPoint. He does beautiful drawings with a 6-inch f8 refractor. Been doing the same technique for 50 years. He mails them to me. He types up a little synopsis of what he has seen. I type that up, hopefully right the first time. And again, you don't need any technology to do this. But on the other hand, you don't need a telescope either. You could just go to the Lunar Reconnaissance Orbiter and look at their images and really do some studies, as Dr. Cook showed us yesterday.
We're going to have a feature by Robert Hayes in the next journal about the crater. I'm not sure how to pronounce it. Euclides or Euclides.
You got it. Yes.
So, anybody else have comments? We got a few minutes left before we introduce the next guest.
Well, we got an early start. So. Time to stretch.
This is Sean Dillis.
Thank you.
I just want to thank David for all the work he does every month and for every journal that we put out. A lot of what goes into the Lunar Observer bleeds over into the ALPO journal, and you're a pleasure to work with. So thanks for all the great work.
Thank you, Sean. Appreciate that. Now look really forward to this afternoon. We're going to have a couple good lunar talks.
And you were worried about running short. You've done a great job with this talk.
Thank you, Ken. Appreciate it.
Tim, do you have any further comments before I introduce the next speaker?
No, it looks good.
Very good. In that case, I will now do a little, let me pull up my screen here. Okay. And behind curtain number one is our current executive director of the board of directors, and that is Carl Hergenrother, who resides in Tucson, Arizona. He is not only the chairman of the board, executive director, but he is the coordinator of the ALPO Comets section. And he is now starting the second of his 2-year term as our executive director. He has been involved in many aspects of comet and asteroid research, including work with the Catalina Sky Survey for asteroid discovery and the NASA OSIRIS-REx mission, which collected a sample of near-Earth asteroid Bennu in the year 2020. Now, on his presentation today, he's going to, let's see here, the ALPO Comets section coordinates, collects, and publishes observations of comets since the start of 2021. This section has received over 1,300 photometric observations and over 900 images and drawings of 134 different comets. These observations are used to produce light curves modeling a comet's change in brightness throughout its observable orbit and identify interesting morphological changes in a comet's coma and tail. Special focus will be given to the brightest comet of the past 18 months, that is the 2021 A1 Leonard, as well as looking ahead to comets predicted to become bright over the next few years. Before Carl starts speaking, I personally want to note that the previous coordinator of the section did a really great job, but he got caught up with some outside projects, and Carl took over and has done one hell of a bang-up job. And those of you who regularly peruse the ALPO journal, specifically the initial section called the ALPO pages or Inside the ALPO, you see his report. I mean, it's just the kind of a thing where you don't want to take it out to the backyard or wherever you observe and use the table and orbital elements of the comets that are listed to just get busy doing comet observations. He's very prominent on Tim Robertson's podcast, and you just can't help but get enthused when listening to Carl talk about this stuff. So I'm going to turn it over to Carl. Take the reins, Carl.
Thanks, Ken. So yeah, as Ken mentioned, I'm the coordinator of the comet section. And what I'll be talking about today is not just comets, but also what the section does, the kind of observations we wish to collect, highlight some of the challenges we run into when we're analyzing comet observations, in particular comet photometry, talk about some of the more recent comets. Basically, I'm just going to look at the last 18 months, all of 2021 through the first half of 2022, highlight a few of the brighter comets and more interesting comets, and then talk a little bit about a comet that is visible now that we can see this summer, at least from the northern hemisphere. Luckily, from the southern hemisphere, you can see this comet and continue observing it for the next couple of years. And then talk about some of the other comets that will be bright, or we hope will be bright and visible over the next 2 years. Oops. So first, I want to give a big thank you and shout out to everyone who's contributed to the comet section. We've had received 43 different contributors. And I'm sure there's a few names I've forgotten, and I apologize if I left anyone off the list, but about 43 or more contributors have contributed just in the last 18 months, which is pretty amazing considering the last 18 months haven't really seen any great spectacular comets. Comet Leonard was mostly, I mean, it was a nice comet, but I wouldn't call it a great comet by any stretch. We did see a big bump up in interest when Comet Neowise was really bright back during the summer of 2020. But activity really hasn't dropped down that much. Even though there haven't been too many really bright comets, there have been enough comets that were bright enough to be seen in small backyard telescopes to keep the interest in comets high. We do publish, we do have some publications at the comments section. I've been trying to well, it's going to take a long time to catch up with the backlog of publishing all of the data we have in the ALPO journal. We did publish the comets of 2019, which focused on the 5 really bright comets, 1, 2, 3, 4, 5, yes, 5 really bright comets that we had the most data for that were at perihelion in 2019. And just to show you, basically the center image and the image on the right, all the people who contributed observations in 2019. Also, I try to put out what we call the ALPO Comet News. And this is really inspired by David's Lunar Observer that comes out monthly, where every month try to just kind of highlight the comets brighter than 12th magnitude that are visible, how they've been behaving recently, how their brightness has been changing, make predictions as to how bright we expect them to be for the coming month, and when they're observable, where they're observable, as well as highlight some of the new discoveries. So I try to put that out. Luckily, it doesn't have to run as long. It doesn't run as long as David's, so I actually have some time to sleep, but it does run about 20 pages or so every month. If you want to find this, you can go to the comments section subpage at the ALPO website. There'll be a link to it. And I also post kind of I do post a smaller version of this at Cloudy Nights, and we do have a forum for every single month where we discuss the comets. So if you just kind of do a search for ALPO Comet News at Cloudy Nights, you'll find the forum specifically for this month's Comet ALPO News. So what does the comments section do? So really, we're interested in collecting and analyzing any data you have on comets. And in general, most of these observations fall into a few categories. Photometry. The comet section still heavily depends on visual observations. So actually going out and looking through the eyepiece and determining how bright a comet is relative to background stars is something that really the majority of our observations are. We also receive what I call digital photometry, just to differentiate it from visual, which is basically just measuring the brightness of a comet with CCDs, DSLRs, CMOS detectors. And usually that's measuring what we call the total magnitude, which is the entire coma. Though to a lesser extent, we do get photometry that just looks at basically small aperture photometry. It's just looking at the very, very inner region of the coma. We still get lots of images, which is really good. And we do get drawings and sketches. Most of those images, drawings, and sketches are CCD or CMOS images. We do get drawings themselves, and I'll talk a little bit about that later. And some people just send me textual descriptions. They don't send images. They don't necessarily send photometry. They just say, I looked at this comet, and this is what it looked like. The tail was off in this direction. It was this long. The comet was condensed or not condensed. And those are really important as well. So when we do photometry, remember yesterday, Richard gave a wonderful talk on photometry of solar system objects. Comets kind of add a few more complications to your typical photometry. For one thing, they're diffuse objects. They're not point sources, or at least they're not objects that have a sharp boundary like a planet does. And they move, which also makes things a little bit difficult. So the hardest thing, especially with CCD photometry, is really determining what you measure. And what I've shown here is the same comet. This was all taken with a small 72 millimeter refractor, the one over there. And this is Comet Leonard, which was the nice bright comet about 6-7 months ago. And if you look over here on the far left, what you have is how most people would actually kind of display a comet with a linear scale and make the background look dark. Now, this is a whole bunch of images that I've co-added. So in fact, the stars are barely there, but I've minimized the stars, almost made them go away, but you can see little streaks where the stars were. That's why you're not really seeing stars in the background of these two images. So you've got this dark background, but all you're seeing is the very innermost part of the coma and a little bit of tail. If you use a log scale, things get a little better. You see more of the coma and more of the tail, but really you have to stretch the display in the log scale. And you can do this also in the linear scale to really pull out a little more of the outer boundaries of the coma going into the tail. And what I actually try to use personally to determine the full extent of the coma is I plot up the isophotes. Isophot is basically a line that's connecting regions with the same exact brightness on an image. And what you can see is that the coma actually extends even further out than what you would detect with this particular image. And if I were to take this image, and what I usually do is I figure out the extent of the coma by drawing a line perpendicular to the sunward direction. As you can see, the tail's going up to the upper right, so the sun is down to the lower left. And then I measure everything within this aperture. So as you can see, you would never, if you look here on the far right with the linear scale in the dark background, you never would have thought of measuring a coma that far out. You probably would have had an aperture that was much smaller. So that is one of the difficulties we have in kind of merging together all of these various data sets, is making sure that folks are measuring as much of the coma as possible. And that's not always possible, depending on what telescope you're using, depending on the focal length, the aperture, depending on what your exposure time was, what wavelengths you were looking at, you know, how bright your sky is. So one thing we end up having to do is try to make corrections to the data. Now, in general, I don't like making corrections to data because you don't know if what you're correcting is real or whether you're even just adding more noise into the system. But it's been well known for many, many decades that the larger the, at least for visual photometry, the larger the aperture you're using, the fainter the comet appears. So there's a thing called aperture correction, and it's basically just a linear relationship between the diameter of the aperture and how much of a correction you need to make for your photometry. And there's different relationships for reflectors versus refractors. And that was published back in the 60s and 70s, mainly by David Heisel, who's the first ALPO Comets coordinator, Charles Morris, who was heavily involved in the Comets section as well back in the 60s and 70s. And I was able to replicate their results using the current ALPO Comets section data. And it was close enough that it wasn't worth changing what they had found many, many decades ago. So what I do with all the visual data is I do this aperture correction. And then after that visual data has been aperture corrected, I take all the visual data as well as the CCD data, which hasn't been aperture corrected. I plot them all up, go into my Excel spreadsheet, I plot them all up, and then I kind of eyeball and move each individual observer's photometry up and down until they pretty much come close. And for this particular comet, which was 64P Swift-Garrels, which is a short period comet, you can see you end up with uncertainties on the order of 3 magnitudes between the brightest and the faintest observers at certain points in its orbit. And then by doing the aperture correction and kind of producing personal biases for each observer, you can knock that down to maybe about a magnitude or so scattered. So that's what I do for each comet. Some comets, sometimes it works better than others, but it is what it is. So let's talk a little bit about the comets of the past 18 months. So as Ken mentioned, we received over 1,300 photometric observations, both visual and digital, since January of 2021. The majority, over 80% of the observations were visual, about 17% were digital. For images, we're about at 900 images were submitted in that same time frame, of which only a small fraction are visual, though I do really want to solicit more visual drawings and sketches of comets. For one thing, there's a lot of details you can see that sometimes you can't even see in CCD images unless you've got a very long focal length imager. And also when you're comparing objects from today with objects that were imaged 100 years ago, you need to compare visual to visual because they didn't have CCDs back then. So they weren't seeing the same kind of detail you see now. So the brightest comet of the last 18 months was Comet Leonard, which was the C2021 A1 Leonard, discovered just north of here, Catalina Sky Survey, where I used to work a long time ago, and where Rick used to work as well. And it was discovered back at 19th magnitude. Most comets nowadays are discovered far from the sun when they're faint by the various professional surveys. And this comet looked like it was going to be really interesting. It had an orbit that not only took it relatively close to the sun, 0.62 AU, but it was going to pass close to the Earth at about 0.23 AU and almost directly between the Earth and the sun, where the phase angle, which is at the sun object Earth angle, got up to 160 degrees. That's high enough that you would actually get forward scattering, where the dust preferentially scatters light forwards. If you ever looked at a beam of light shining through a window, or even back in the days when we used to have overhead projectors, you would notice, depending on the angle you were looking at that beam, you would see a different amount of dust. And if you were looking kind of in the general direction back at the light source, you would see a lot of dust. That's forward scattering. That's the dust preferentially scattering light forward. So the hope was that Leonard would become a nice bright object, maybe even a naked eye object. But Leonard kind of threw us for a loop. It was brightening slowly, then brightening rapidly, then brightening slowly. And then as it was observed in the morning sky, as it dropped close to the sun, it kind of stopped brightening intrinsically. It was still getting brighter because it was getting closer to the sun, but its level of activity seemed to be dropping off, and it wasn't getting anywhere near as bright as we were hoping. And then it ends up very close to the sun. We lost it for a few days. And then when it popped out, instead of being the 5th magnitude object it was when we lost it in the morning, it pops up around 2nd magnitude. And then the comet starts experiencing a number of outbursts. It seemed like every 3 or 4 days, it would have a 2-3 magnitude outburst. And it's possible this 3 to 4 day period is because that is the rotation period of the nucleus. That's still work that needs to be done. But it ended up being a nice comet, visible fairly low in the evening sky. But as you can see here, there were, this is an image taken from the island of La Palma, had almost a 30-degree tail, at least for imaging. Nice gas tail. For most of us, of course, we didn't see a 30-degree tail. I think through my binoculars, I saw more of like a half-degree tail or so. But it ended up being extremely photogenic comet. This is one of the first images we received of it just shortly after discovery. In fact, a few days after discovery, when the comet was still at 19th magnitude. It passed by a few nice deep sky objects. So it had a few kind of photobombed, a few globular clusters and galaxies, which was nice. And then at its best, right after, this is before perihelion, but after that close approach to the Earth, it had a nice dynamic tail. And you can see changes almost every day in the inner coma as it was experiencing these outbursts. And then about mid-January, it ended up going to small solar elongations again, and we lost sight of it. And when it popped out again a few months later, all that was left of the comet is this kind of ghost trail. So it does look like the comet may have completely disintegrated, possibly as a result of these outbursts, or perhaps these outbursts were a sign of the nucleus falling apart. But what's interesting is that even though the comet's disintegrated, most comets, when they disintegrate after a month or so, there's nothing left of them. You've lost basically any evidence that the comet was there. But for a few months now, we've been following this dust cloud as it's receding out into the outer solar system. So that was Leonard, which was definitely the best comet of the last 18 months. Another comet that we were really hoping would be bright was this C2021-03 Pan-STARRS. It was going to get really close to the sun, about 0.29 AU. That's similar to what NEOWISE did 2 years ago. We knew it was intrinsically faint, but there was hope maybe it could become a borderline naked eye object. And then it, kind of like Leonard at points in its inbound arc there, just wasn't brightening. It just was not getting bright. So that did not give us much hope for this being a bright comet. And as it turned out, it did not become a bright comet. But it was still interesting in that for a few months before perihelion, we couldn't see it from the ground. But other spacecraft, mostly the chronographic spacecraft looking at the solar corona like SOHO and STEREO, were able to image it. And they saw it as, SOHO saw it as reasonably bright, which got our hopes up. And then STEREO saw it as kind of a streak, which made us wonder, did this comet fall apart? But as it came out, it looked like the comet actually was still in one piece, just faint and diffuse. So here was a comet that was really small, was intrinsically faint, probably should have disintegrated due to its small perihelion distance, and it didn't. It survived all the way through, unlike Leonard, which was a much more active and much bigger comet, or at least we think it was a much bigger comet. There were quite a few short period comets that were observable over the last few months. 67P, Churyumov-Gerasimenko. You may know this one because that was the target of the Rosetta mission, the European mission that went in orbit around the comet and observed it. So it's probably one of the best studied comets we have out there. And it peaked around magnitude 8, which was pretty nice at the end of the year. Just to show you an example of some of the images that can be made with relatively small apertures. This was actually taken with a 51 millimeter refractor, a good refractor, but still a 51 millimeter refractor, though it was approximately a 2.5 to 3 hour exposure. And what you see here is not just the comet itself. You've got the gas coma, which is that blue-green. You got the nucleus is in the middle of the brightest part, got a bit of a dust tail going out. And then you've got this line that kind of goes through the nucleus and extends out either end of the comet and basically extends many, many degrees on the sky. That is actually dust that is these are large particles, basically future meteors or meteoroids that are being spread along the orbit of the comet. Now, 67P doesn't come close to Earth, but if it were, you basically would be seeing, Gerasimenkids or 67Piids meteors if we were actually to go through its orbit, which is pretty cool. And we've known about these, of course, for years. They were usually seen in infrared images, but as more and more observers are using wide field, small focal length instruments, we're seeing these dust trails more and more often on more and more comets, especially short period comets, because they go around multiple times. So they have multiple passes to lay down this trail of material. 104P Kowal was a nice surprise, a short period comet that was expected to get maybe 11, 12 magnitude. It got up to around 8th or 9th magnitude. Discovered back in 79. It was actually visually discovered in 73 during an outburst, but unfortunately, due to communication issues, it was lost before that was confirmed. One nice thing about this comet is that its perihelion distance keeps dropping from discovery even to now. And as a result, 104P, and this is a plot of its past and future orbital evolution, where you've got the triangles are its perihelion distance. The blue circles are its closest approach to Earth during each of these returns. And then the Jupiters are basically when it has close approaches with Jupiter. And what you see is through the remainder of the century, this comet will actually be one of the better observed comets because it now has a perihelion distance less than 1 AU and allows close approaches to the Earth. So this object will be kind of like how Vertinen and Hartley 2 are now, where every time, or Giacobini's Inner, where every couple of years we see it as a nice bright short period comet. Kowal will be entering that class for the remainder of this century. And then 45P Honda-Mercash-Pagesikova. This is a comet every 5.5 years or so, comes perihelion. We've observed it 14 different times. This was not supposed to be a good return. The last 2 returns were excellent. This was not supposed to be a good one. And yet this comet was about 3 magnitudes brighter than expected. And I'd like to highlight Michael Olesen, who lives just north of Tucson here. He does a great job of just pushing his instrumentation, whether it's co-adding with his C14 to get down to 20th magnitude, or in this case, using a 50 millimeter lens when the comet was only a few degrees above the horizon, and really going out of his way to detect this comet. And because of his observations, there were actually professionals that then studied the comet because it was an outburst. And I never would have considered trying to find this comet visually. And because of his observations, I went out and eventually I was able to see it on a few nights visually in the bright twilight. And this is just kind of highlighting a few of the other comets that are out there. I only hit a very small sample of them. The interesting thing on this page is actually over here, 12P Pons Brooks and C2022E3. Remember those two for a few slides from now. But what is visible tonight? Right now we have a comet called C2017 K2 Pan-STARRS. One of the most interesting comets we've discovered in a long time. When it was discovered back in 2017, it was out at 16 AU. So it's, between Saturn and Uranus. Analysis of its dust suggests it may have been active as far out as 35 AU. You're talking Neptune-Pluto distances. How is a comet even active out there? Let alone how does it have enough energy to throw large particles off the surface that we can see it. So this comet is a bit of an enigma because its nucleus is large, but probably not super large, not Hale-Bopp large. And now that it's near perihelion, and perihelion is about 1.8 AU, and that's in December, it's only going to get up to 8th magnitude. So it's just amazing that this comet was active so far out. Right now, and it does show a little bit of nucleus features. These were images I took on back-to-back nights, so they look like the exact same images because the features aren't changing. They don't appear to be changing quickly. And right now, K2 is evening side, near opposition on the evening side, moving south through Ophiuchus into Scorpius. Unfortunately, here in the Northern Hemisphere, we're going to lose it in September, but it'll be observable from the Southern Hemisphere for a long time. So just looking further ahead, what other comets are observable? And this goes out about 2+ years. What's highlighted or bolded, that's when the comet is observable from the Northern Hemisphere, here at the mid-latitudes. If it's not bolded, it means it's observable somewhere, just not basically for most of us in the Northern Hemisphere. And the number is how bright it's going to be. So the next nice bright comet is one of the comets I showed just before, this one over here, C2022 E3 ZTF. ZTF actually stands for the Zwicky Transient Facility. It's a group that's using the 1.2 meter Schmidt on Mount Palomar. And it's looking like this comet will brighten probably between 4th or 6th magnitude in January, February next year. Perihelion in January at 1.11 AU. It does come within 0.29 AU of the Earth on February 1st, which was nice, which also means it's going to be well placed in the opposition sky. So it's one that you don't have to fight twilight to get an image of. And I'll talk more about these probably during next year's talk, but we have 2 Halley family comets that come around every 70 years, so once in a lifetime comets, 12P Pons-Brooks and 13P Olbers, which Pons-Brooks may be the best comet of 2024 at around magnitude 4. And hopefully there'll be new bright comets discovered that will be even brighter than the ones that are plotted here. So thank you.
Yeah, thank you, Carl. That was a very interesting talk. I just calculate the Hellish Comet. Now that next year will be very close to 1 billion, which is the furthest point away from the sun in orbit. Is there any chance that the Hubble Space Telescope or even the James Webb Telescope are able to image the Hellish Comet the furthest away as possible?
So it's interesting. So it's going to be around 35 AU in December, which is aphelion, which is where that C2017 K2 actually became active, about that same distance. I have looked at the James Webb programs. I don't see anybody planning to observe Halley, even though they probably could, though it'd probably be about 29th magnitude. They are planning to observe both with imaging and photometry Hale-Bopp out at like 46 AU. And Hale-Bopp, the thinking is a 50-60 kilometer nucleus, so even much larger than Halley. So the possibility that they're not only going to be able to image it, but even get spectroscopy of its surface. And hopefully by now, Hale-Bopp should be inactive. So we may be able to directly measure the ice on Hale-Bopp is one of the observations I'm really looking forward to seeing coming out of James Webb.
You know, Carl, if you ever give up on astronomy, you could work for the United Nations. I love the way you have no problem with those Eastern European names.
Okay, so I was talking at a ACM meeting, Asteroid Comets Meteors. They have them every 4 or 5 years. This was in Cornell, and it's basically a joint U.S. foreign meeting. It's not just U.S. comet asteroid meteor people. And I was giving a talk, and I'd gotten to know the Czech Slovak crowd because my grandmother's from Slovakia, so I got in good with them. And I get up there, and I'm talking about this comet, and I say 45P Honda Mercash Pajasakova. And I look down and they're all in the front row and they're just shaking their heads. And I'm like, and they're like, Pajasakova. Oh. And honestly, I may have flipped them. I may be pronouncing it the wrong way, and how I had it before is the right way. But yeah, I learned from experience not to pronounce that particular word correctly, that particular name.
Well, having grown up in Cleveland, where those names are not that uncommon,
Mhm.
very interesting that I can just rattle them off. I grew up in the Slovak area. Anybody have any more questions? Okay. Thank you, Carl.
Thank you.
And at this point, I'm going to move on to our next speaker, Richard, who goes by Rick, R-I-K, Hill, who was also in Tucson, Arizona. I don't know if he's on the other side of town or if he's anywhere near Carl's house.
Just down the street.
Down the street. Rick and I talked about a couple things in the past. We both have common interest in the old Criterion dynoscopes. Rick was born in the Metro Detroit area of Michigan. He got into astronomy in about May of 1957 when a substitute teacher at his two-room schoolhouse, wow, in the country, brought a 1.6-inch unitron refractor to show the transit of Mercury, but instead showed a lot of sunspots that day. Then in 1974, Rick married another amateur astronomer, that would be Doris. After selling her telescope, and you know her as the meteorite section coordinator, that would be Dolores Hill. And then after a 35-year career in astronomy, Rick retired from the Catalina Sky Survey, where he was with the NEO Asteroid Search in 2015, and has been very busy with the ALPO solar section that he himself founded in 1982. I think Walter approached Rick about starting the solar section, but Rick will talk about that. His talk called Blinded by the Light, also the title of a great song, Early Techniques in Solar Observing, and it's going to highlight some of the scary attempts to observe the sun telescopically. Take it away, Rick.
All right. I hope you're seeing the whole screen. I've got a bar going through the middle of mine.
It looks good.
You're good.
Oh, we're good. Okay, then I'll just ignore that bar. Okay, well, this is about early techniques in solar observing, telescopic solar observing. I should have added that in there. I'm not going to talk about visual solar observations of sunspots, which occurred for centuries before that, are very poorly recorded, and we know little about them. And I do not have control. Here we go. So I just want to remind you, solar observing is very dangerous, and the same old caveats: never look at the sun without proper filtration, even if you're just looking up at it, or even at sunset. And we'll talk about that in a second. It only takes a second. And so you don't want to be doing anything silly that's going to last the rest of your life. The telescopic era began in the early 17th century with 4 claimants to be the first to see sunspots. And you're going to learn something interesting here. At least it was interesting for me, because for years I thought, oh, Galileo was the first one to see sunspots, of course. And not so. We have Thomas Harriot in England, who started observing the sun on December 8th, 1610. He made 699 observations with a telescope we know nothing about. It was probably a small refractor, probably of Galilean construction. But he reports magnifications of 10 and 20, and how he measured that, we don't know either. He probably just looked through it and said, well, it looks about 20 times closer. And he observed directly with no known filtration. He would observe at sunset or sunrise. And this just is such a scary thing to think about. But that became common, but he probably used tinted glasses of some sort. I can only imagine, you've seen glass from this period. It's got swirls in it and everything. So who knows what the filters were like. But he has no reported eye injuries. This is a page from one of his notebooks that shows his sunspots of very limited value. I mean, just we don't even have orientation on there, which way is north or anything. The reading here is interesting if you can read it. It's slow going, but you can make it out. The English hasn't changed that horribly much since his day. And it says things like, observe the sun through colored glasses. He preferred observing with the unshaded eye through mist or veiled clouds, or the sun veiled by clouds. It's scary to think of that, at least in Arizona. But it must have been blinding. And he says here that all being clear in the sun, I saw a great spot with 10 and 20 power, but no more. My sight was dim for an hour. This should send chills down your spine. But John Greaves at Oxford, not far from him, measured the sun's diameter, damaged his eyesight such that he had the appearance of a flock of crows flying together in the sky, probably small retinal burns, for some days afterwards. I've experienced this myself when I had a solar filter crack on me in a 6-inch reflector. And it cracked, and I had just a little sliver of sunlight that got through, but I saw the crows in the sky. So it is possible to observe this, and you don't want to do that. Now, Fabricius, his father was an astronomer who had a heralded career working with Tycho and Kepler. So really, Fabricius himself had no choice but to become an astronomer. His father was a preacher in the town of Ostend, but he began, now remember, Harriet began in December 10th, 1610. Fabricius began on March 9th, 1611. He began observing the sun. And he too used direct vision at sunset and sunrise with smoke glasses or colored glass. Smoke glass they like to do it over tallow candles because they provided the most even coating of smoke. But they also like to use over the oil lamps of spermaceti oil, which we can't get anymore. That's whale oil. And he used the direct observation and made the scary suggestion that by gradually introducing the sun's image into the field of view, his eye grew accustomed to the brightness. And again, that should send shivers down your spine, doing something like that. And yet there's no reported visual impairment, lasting impairment from doing this. He eventually settled on projection for his observations, which is pretty much what would naturally happen because you have a telescope there pointing at the sun. You've been looking through it. You pull your head away and, oh, look, there's a nice little image of the sun on the floor. Why don't we look at it that way? This is where he observed. This is his father's church where he preached, and he observed from this tower, and he made several observations that the sunspots are not transits of planets or stars, which Galileo disagreed with him, thought he had interpreted it as transits, and he determined that they were on the sun itself, which is an important observation. He also noted that they moved at a constant speed across the sun, implying solar rotation, because they appeared 2 weeks later. They must have had a very good solar maximum going on at this time. And you'll see more evidence for that shortly. Christopher Scheiner was a Jesuit priest. He began observing the sun in April 1611. So far we've got December 1610, March 1611, and April 1611. He was not allowed to publish under his own name by his senior. And so he had to share his observations anonymously with Mark Wetzler, a merchant in Augsburg, and who quickly shared those with Galileo, and Galileo ran to publication. This is very similar to what happened to Darwin when another young fellow came up with the theory of natural selection, And Darwin had been working on it for years, and so he ran the publication, had both his papers and the other fellow's papers published simultaneously in the journal. And it's the same kind of thing here, and he published his own observations. This is what Shiner published him, the Rosa Ursina, which is the rose and the bear, which was the sign of his benefactor, the Duke d'Orsini. And I love this one little picture here of the bear sitting in a cave of roses, and the bear is projecting an image of his son onto a little tablet. I just love that picture, and it shows the Rosa Ursina over the cage or over the cave. And this is the first page of the book, absolutely spectacular lithography. And this page, this is the second page over here. And I want to zoom in on that. It shows a couple of interesting things. Here we see probably Shiner looking at through his telescopio, and he's looking up in the sky, but I see the clouds here. So this is probably an expression of frustration with the weather he had in Austria. But over here, note, he's looking at helioscopio. He is looking at the sun directly. And that is just so scary, because over here, you also see at the base of the obelisk, they've got a projected image of the sun. So they have the safe technique available to them, and why they even messed around with direct observation is beyond me. This is his sketch of his telescope. This is the telescope right here. That's the telescope. The rest of this is just to hold it steady and provide a drawing tablet for the images. Later on, he had this telescope constructed, where the length of this leg right here and its position is what determines the altitude for the telescope. Very sturdy. This is the telescope itself right here, mounted on there. Notice it's a much longer telescope now. So it provided a better image, and it's projected onto a table down below. And this was all published in 1630, but the observations that were published in 1630 were the ones from 1625 to 1627, not his earliest observations. He had really developed his techniques by that time, so he had a very good technique for presenting sunspots. And you can see he follows these sunspots across the sun. And you can see he's even demonstrating faculae here, as well as the sunspots. As you get near the limb, you can see those white clouds that are involved with the sunspot groups that are faculae. Absolutely spectacular solar maximum they had going on at the time. And you can see all the sunspots here. And he clearly understood solar rotation, regardless of the fact that Galileo argued with him about it. Now we have Galileo himself. He began observing the sun in June 1611. So of the four early astronomers that observed the sun telescopically, he was the fourth, even though he claimed to be the first. He was an irascible character and made a lot of claims to priority in many things that were not, he was not the first. Interestingly and important, he did not lose his eyesight to solar observing, as is commonly believed. He had ordinary cataracts and glaucoma. Ophthalmologists have written papers on this, on his observations, and they've determined that he just had normal cataracts and glaucoma for a man in his 70s. Hello, I've had them. And I don't have glaucoma, but I've had cataracts in both eyes, and I've had retinal tears. And so, you know, it's just natural course of getting older. But he also had a thing called keratocanthoma. They're pretty sure of that now, and that can be seen right there. Notice this little mark? We'll discuss that more in just a second. He possibly observed the sun directly, but he eventually settled on projection because of his student Benedetto Castelli, who recommended projection. Here's one of his projection images. He disputed Shiner. He claimed that Shiner was saying that the sunspots were transits of Mercury, and Shiner wasn't, quite obviously from his observations. but you can't have an argument with somebody when you don't disagree with them. And so he argued that that was what he was saying. Now, he hesitated to publish right away because he had a friend, Cardinal Maffeo Barberini, who for years he shared his scientific observations and experiments with as Cardinal Barberini. But when Barberini became Pope Urban VIII, he became a different person. At that point, he was representing the church, and he represented a whole different paradigm of that at that point. And that's when he and Galileo fell into disagreements. And so I won't go into that in any detail here. It's a fascinating story. But Barberini is two different people, one before Pope and one after Pope. There is no known attempt to coordinate the observations of Galileo and anyone else, whether it be Scheiner or the poor observations of Harriot and Fabricius. So we really can't say anything more about the sunspots. Now, this is an early portrait of Galileo. Going back in the portraits, we see that spot right below the eye. That is not a mole. Ophthalmologists have gone through and looked at the portraits, and you can do this yourself. There's many portraits, and it shows up more and more, and it's under the left eye. And they claim that this is the keratocanthoma that Galileo had. Further evidence for that is, notice the two eyes are not looking in the same direction here. That the left eye is more open and looking in a totally different direction than the right eye. That is another symptom of keratocanthoma. And as a result of that, a group of the British and Italian scientists want to exhume the body for DNA tests. And here you can see that the eyes are, again, not looking in the same direction, and that the left eye is also dilated. These portrait artists at the time were realists. So these, you have reason to believe these is almost photographic evidence. So they want these DNA tests, and this is where he's buried. Nobody's going to open that tomb. It's just not going to happen. That's cemented in. And but it's not necessary. Exhumation's not necessary because before he died, his middle finger was removed, and he has been giving the middle finger to the scientific world for centuries now. And there's plenty of material here. All they need is a little piece like down here for DNA tests. So hopefully they'll go ahead and get their DNA from this, and it would be, of course, that assumes that this is Galileo's finger, but there's no reason to doubt the provenance on that. From Webb, we have some other things here that much depends on the dark glass of the solar cap, which is screwed on the eyepiece, and red is often used, but dark green is better. Red transmits too much heat. This is from Webb, his Common Telescopes book of 1859. Many of us have copies from the Dover edition in 1963. Cooper, also at Markey Castle in Ireland, used a drum of alum water, which was dark, and he put that in between the eyepiece and the telescope, and then used dark spectacles on top of that, and he could endure the whole aperture of 13.3 inches. Magic word here is endure. I cannot imagine what that must have been. With large apertures, a plain surface of unsilvered glass plate placed diagonally before the telescope was suggested by John Herschel so as to reflect only a small fraction of light and heat. A good technique, but they didn't have the glass quality back then to do that. It requires very good plain glass. And then Mertz of Munich did the 4 polarization surfaces, not safe. It passes UV and IR light to too much of a degree. But they also suggested in that book a Barlow lens, carefully silvered, is said to act admirably, but no evidence of anyone that used that. It is an excellent technique, and Criterion Manufacturing latched onto this back in the 1950s, but they used chrome on their Barlow lens. Gives a nice orange image of the sun. This has several benefits to the screw-on eyepiece that the Japanese send out with their telescopes. That is, the focus of the telescope is down in here, as is the focus of the eyepiece, whereas this is shoved into the light path quite far, and as a result does not heat up as bad. I have used this with great results for many times with a 6-inch reflector. It works great. And if you can get one of these for solar observing, they're wonderful, but they're hard to find. Now, William Herschel, he was preparing for a transit of Mercury, and he got clouded out mostly in 1802, but got interested in solar observing. It's not clear whether he saw the 1799 transit of Venus. Not transit of Mercury, transit of Venus in 1802 and 1799. He went on with tests with his 9.5-inch telescope that he wanted to use full aperture on the sun. He did many experiments with colored glass and smoked glass, and you can read these online. I'll have the references. It's very scary experiments in many cases. The filters broke in many cases while he was using them. Hopefully he wasn't looking through the telescope at the time. But again, there's no records of any eye damage. He also used different liquids, and he put this in the telescope. Now remember, he had altazimuth reflected telescopes. So he'd put this in the eyepiece, the horizontal eyepiece holder, and this little picture, these are not drawn to scale, would fit in here, and he put different liquids in it and try those. His favorite was dark red port wine. Of course, that's my favorite too. I love port wine. And so he didn't say what he did with the port after it had been sufficiently warmed by the sunlight. There was an experiment number 27. He says there was no occasion for smoke. The sun appeared a bright scarlet color, and there was an intolerable sensation of heat that took place immediately. He had already hit on an early experiment with dark green filters that worked well. And why he just didn't stick with that, he didn't like the green color of the sun through those filters. So he never would have liked a Japanese refractor. But he had the solution in his hand, but he wanted yellow or red. So that's what led him to start experimenting with the colors and taking thermometers. You see 3 of them here. And he'd put them in the spectrum. He put the middle thermometer in the spectrum and use the other 2 thermometers outside the spectrum as control temperatures. And he would move along the spectrum measuring the temperature. And that's how he discovered infrared and why his red filters didn't work well. No, he never used the 40-foot telescope for solar observing. That would have been insane. But insane is coming. This is the prism he used for those experiments. It still exists in one of the museums in London. His son, of course, came up with the Herschel wedge, which is a very good way, but it also has its dangers. I've seen a Herschel wedge used with an 11-inch refractor. Very scary. Roger Tuthill was there that day. He had just given or was about to give a talk. It was at Riverside. And he bent over to use it, and they didn't have the baffle in, and he burnt his necktie with the light coming out of the Herschel wedge. So these are not to be taken lightly. Here's a couple of commercial Herschel wedges right here. Now, William Rudder Dawes, I'm going along, I'll finish as fast as I can. He's cradling his first telescope right here, but this was his 6-inch telescope, very well mounted, very sturdy mounting. It's a Mertz refractor, and he did his solar experiments with that. Here's one of his papers in 1851 on solar observing, where he uses a field bar in the eyepiece. And the best I can figure is he's blocking out the central portion of the aperture of the telescope and using just the outer part of the aperture for observation, so he retains the full resolution of the telescope, but he kicks out most of the light. And as he says, the rest of the light is being filed away, as if it was another zip file or something he could put away. Well, a year later, he writes a revised article on this, and suddenly he's not doing that anymore. He doesn't mention the field bar again. And instead, we have this description of an eyepiece device that has an aperture limiter there, a filter wheel here, and then back here, another aperture limiter with very tiny apertures. You can see this one. There's another one down here that's 132nd of an inch, I believe. But it starts with a white ivory. He loved using ivory. An ivory block in the beginning before this aperture wheel even. And the whole thing on the telescope looks like this. Now I want to point out the eyepiece here. This is important because most of us would call the whole thing a solar eyepiece, but this is what Dawes refers to as the eyepiece. Here's a modern photograph of that same device. And you can see the one limiting apertures up here and the filter wheel back here and the other limiting apertures back here. Dawes studied the interior of sunspots. You could not do the whole sun with this. And he said here that in order to test this, he goes over to Lascelles' 20-foot reflector, which at the time, this is the one that wound up in Malta, but at the time it was in Liverpool before it went to Malta. And they used the whole aperture of 24 inches on the sun for 2 hours in the middle of the day with no injury. That's a measurement of success. Nobody got injured. And he says the eyepiece became no more than sensibly warm. He's talking about the very back eyepiece. I cannot believe those front apertures didn't become griddle hot. Because that's a 24-inch telescope. And so he goes on to say there's no reason to fear if it were applied to Lord Ross's largest reflector with the whole of his 6-inch speculum in use. A crazy suggestion. I have calculated what the temperature of this image would be at the focus of that telescope with only 60% efficiency in both the primary and secondary mirrors and reflection. And it's around the temperature of the surface of the sun. So no, this is not a good idea. And I'm glad they never did it. I looked and I think the eyepiece would have just simply melted or exploded. After those experiments, we get to Christopher Carrington, who used projection. We know him for Carrington rotations. I'll recommend a book at the end of this. Tragic life, absolutely tragic life. It's amazing he made the mark he did. This was his house and his observatory. He eventually had to sell them so he could go back and work at the family business of a brewery, which he hated. And then there was Heinrich Schwab. Of course, we all know him for the sunspot period. And he used direct vision with an eyepiece built by Fraunhofer. Must have been safe. He used it for decades. This is Christopher Carrington's observation of the white light flare. This changed astronomy in ways I hope to illuminate in a later talk. Absolutely fascinating what this one observation did for solar astronomy and for all our understanding of the sun. And after that, we had photographic observations. And so solar filtration settled down to becoming something more reasonable. Here's an image with that photoheliograph. And the first user of that photoheliograph, and she's just now starting to be rediscovered, was Elizabeth Beckley. She did most of the observations with this for its first 13 years of existence. And here's the references I used for creating this paper. I would point out this is the William Herschel reference here that discusses most of his eyepiece experiments. And recommend the book, The Sun Kings. Absolutely fantastic book, very well written, very easy to read, and goes into the life of Christopher Carrington to a great degree. So with that, I thank you very much. I'll leave this up so you can sketch this down. And during the break, I hope I can put up a slide of the my email address for you. Any questions?
Thank you, Rick. I hope we're gonna, well, what we really need to do is to try and make these various talks available as sort of a compilation for anybody that wants to download them. We'll see what we can work out.
Yeah, they're all available on YouTube at any time. And also, Rick, if you want to put your email address in the chat, that would be a good way for people to see it as well. Great.
Okay, we're going to move right along now to our final talk before we take our break. And I'm glad to present Frank Melillo. Frank lives in Holtzville, which is on Long Island, New York. And he's been more active in ALPO than in any other national organization since the beginning of his career in astronomy. In the year 2001, Frank became the Mercury coordinator for the ALPO. He followed, I forgot the gentleman's name, but he passed away only not that long ago. David, that's right, Mr. Baum, great guy. The same year, that is in 2001, Frank received the 2001 Walter Haas Observer Award for the most outstanding contribution to planetary astronomy. His talk today will be, guess what? What's up with Mercury in 2022? And he's going to highlight the importance of observing and imaging Mercury in 2022. I would like to note that Frank is the ultimate enthusiast of Mercury, and he really needs a lot more of you out there to contribute to his reports. So Frank, you've got until 3 o'clock.
All right, thank you, Ken. First, everybody see the screen and they hear me? Yeah, great. Okay. Hello, everybody. And it's really a pleasure to see many of you guys on the screen. But to be honest, I'd rather present this in person, but unfortunately, it's not happening right now. Over the years, I'm pretty sure many of you may or may not know that the Mercury coordinator since 2001 that Kent mentioned. And all the time, I try and encourage many people to observe Mercury. When it comes to planetary observation conversation, I always mention about observing Mercury and all. And they always said that, like Mars, Jupiter, and Saturn, it's so well observed. And actually, Mercury is a neglected planet. And also, it's a smaller planet and it's the least conspicuous of the naked eye planet. But, every time I go to the star party, I always mention about, planetary observing. There's always a planet to observe in the sky. And as a matter of fact, next week I'm going to Stelfane, and I'm very sure that I'm going to run to some people who talk about planetary observation. Of course, they have a 9-inch Scumpman refracted telescope, and they always pointing at the planets. So we're going to have like Saturn, Jupiter, a little late in the evening to observe them. So I'm pretty sure we'll talk about. All right, I'm going to move along.
Frank, are you muted?
All right, you hear me? Okay.
Yeah.
I'm at the front. Okay, yeah. I'm pretty sure you're well known that this is the front page of the current ALPO journal. And what you see here is all the planets light up. We were treated of the planetary lineup in the morning sky before sunlight between late June and early July. And you have Saturn here, you got Mars, and you got Venus, and you got Jupiter, and also you have a crescent moon. Okay. Oh, what about Mercury? Well, unfortunately, Mercury was in the evening sky at that time. This was taken April 27th by Mark Woodwright in Atlanta area.
Yeah.
So that's pretty nice pictures, yeah. But the next picture I want to show that my good friend of mine, Stan Honda of New York City, he's a well-known wide-angle photographer. He takes pictures of the eclipses of the sun and the moon and any astronomical events taking place in the sky. Well, this photograph, he managed to take all the planets line up at late June. The time you see Mercury on Saturn this side here, Jupiter, Mars, and Venus, and the crescent moon. And I asked him, what about Mercury? Mercury was visible at that time too, so it should be all 5 planets. He said, yeah, Mercury is way over there on the bottom left-hand side of the corner, right over there. Oh, right, yeah, because most of the images, take pictures of the planet. Mercury's always left out, always behind the trees, always behind the building, or blocked by the clouds and all. But then the next image is the close-up of the moon, the crescent. There it is, Mercury right over here. It's a little dot. Anybody see that? Okay. Well, this picture was taken from New Jersey. If you go back from the Jersey side, overlooking the Hudson River and overlooking the Manhattan skyline, and you see all this nice planetary lineup in the morning sky. So this is a part of the New York City skyline here, and Mercury was just barely visible there. So that's cool, though. So, okay. Also during that year, in April, Astronomy magazine, they have one of the featured article. The Strange History of Mercury Spots. Now, this was written by William Sheehan. I'm pretty sure many people are familiar with him, but he's also a solar system historian. So he always talked about the past history of the planetary observation, what you see, what they see, what they didn't see, what it means and all. Well, we exchanged an email over the years. Of course, I met him at telephone one year. He came across planning to write an article about Mercury spot, and he contacted me, and I gave him some information. But the idea of the article is that Schiaparelli, he's a well-known Italian astronomer back in the late 1800s. He's, I'm pretty sure many of you pretty sure he knew that he's well known for seeing the canal of Mars, and of course it's followed by Christopher Lowell, but he also recorded odd markings, strange markings on the surface of Mercury. The picture here posed by the 9-inch refractor, Barry refractor at Barry Observatory in Milan, Italy. He devoted his studies on Mercury. Do not part of the article, but what you see here in the middle, that's his sketch. That's his sketch from back in February 6, 1882. That's where he drew of Mercury. Now, what you see on the left, this is the image of the Messenger spacecraft, and on the right, this is the blur image of the Messenger's imaging. So the idea is that that he drew some strange marking, like a figure number 5, if you see over here, okay? And now at that time, on April 23rd, this past April 23rd, Mercury was exactly in the same spot, same longitude, same phase, very similar to what Schiaparelli saw back in 1882. But the next page, he also saw another figure of 5. So every time he observed Mercury, you always see a shape of number 5 here. And of course, this is the very odd image here of the Messenger's spacecraft. This is a very blurry image. Now, the reason they a blurry image because it reduced, degraded the images to equivalent to the amateur-sized telescope. So that's why they're able to compare the resolution of what he saw and compare to the blurred image of the Messenger spacecraft. Also, this is the portion that I wrote, the little box on the side of the article that I didn't mention back in about April 23rd. Mercury appears in the evening sky and will be very equivalent to what Schiaparelli saw back in 1882. And once again, you see the figure 5 here, and also this is up here what Mercury will be at April 23rd. So this is exactly the same surface for what he saw back in 1882. Same longitude, same face angle, same apparent diameter. So on April 23rd. So unfortunately, it was cloudy here, but I did not receive any observation from other people at that day, and hopefully to duplicate to what Schiaparelli saw on that time. And so I don't know, if you look carefully here, you may see a figure 5 here. So there may be some kind of connection. So we really don't know, because every time he observed Mercury, you always see streaks across the surface. So we don't really know. It's a completely mystery, and it's never been confirmed. So that's still a possibility, but more work needs to be done. So this is a very well written article by William Sheehan. Okay, now I'm going to talk to you more about observing some of the great images that we took this past year. Also, I have this article published in this current ALPO journal, imaging of the surface of Mercury from 269 degrees to 100 degrees west longitude. I'm not going to go too much detail about it, but it published this current journal, and this is what I want to show, that it's one of the best work I did on Mercury. And surely I like to present this, and also wrote out the paper. Just briefly, I'm not going to go too much detail. Just briefly, this is what I observed during November 2020 morning apparition, which is quite favorable, visible from this part here. Luckily, I had great weather, great scene, so you cannot ask any better than that. So this is just briefly what I saw here. This is my image here, and this is the image from Messenger spacecraft. What you hear, that's what I'm supposed to see here. Just for example, here you can see some ray craters here. It's very, very prominent now to when doing the imaging, because it's very high reflectivity from the high noon sun from the surface of Mercury, and have a very high reflectivity. And again, the next month, the next image, as you can see here, some of the ray craters. Now, the ray craters, just briefly, you not actually see the crater on the moon, like we see on the moon. Those are craters that during the impact, that shut off all the elements and all, and it appeared very bright. This is equivalent to what you see on the moon, like Copernicus, Tycho, Kepler. You see these rays there, like you see with the naked eye or through the binocular. Well, this is very similar what you see here on Mercury. Okay, this is a part of the surface, and that was visible in my image. And I also indicated some of the marking here. These are ray craters. See how bright they are? And they're very high, very high impact, and they shine very brilliant. During the course of the time. And of course, this is the list of features here. So the next one I'll show you, I made a little short animation, 2-day image here. And the next one here, the 6th image animation. You can follow those ray craters marching across the disk. Now, this is not a rotation, but this is an orbital motion as Mercury going around the sun. And of course, this is the 2-day image in 3 days, and you can actually see those ray craters rotated with orbital motion. And this is really fascinating. I mean, even a professional astronomer wouldn't able to do this as little as 20 years ago. They don't have a technology like right now, but now the amateur able to take over and provide this kind of work. This is true. This is maybe this probably considered one of the first-class amateur work. Okay, we have Tim Wilson. He's a very active Mercury observer back in my early years as the coordinator. Then it seemed like he drifted off a little while, but now he's coming back this year, and he did some images of Mercury back in March 19 and March 20th. And this is the graph that he created and some of the features that are visible. But now these, of course, these features are no longer named, because now with the messengers images, now they have to provide more new names for it. So this is old name that was probably from the 18th, 19th centuries. So, but I processed some of his raw image, and it came out quite well. I mean, this is the image that he took March 20th, and I processed this in a way like it's my image, and it came out pretty good. I mean, as far as the 8-inch telescope that he was using. He's from Jefferson City, Missouri. I never met him, but we always exchange on email, And this is the Messenger Wind Juppos simulator, and you can see very consistent with his image. And those two here are ray craters, which is this one here. This is one of the brightest ray craters on the surface of Mercury, especially on this side. And this is another dark feature. I don't know the name of it. I don't have it with me, but it's got a very sophisticated name. And also you visible here. And there's another lighter region on this side, and which corresponds to this. So this is pretty consistent with one another. So it's just to show you that even though the Mercury has a reputation of the most difficult object to images, but if you plan well enough in advance, you can able to hopefully, you can able to provide this series of studies in Mercury. And also, this past June and July, early this month, morning apparition, was just absolutely stunning. And gladly now I can able to show you this image is just like a month old. First of all, back in June 19th, last month, we started with in the morning apparition, and you can see Mercury already have a nice face there. But the detail is a little hard to see because it showed less part of the surface. Compared with the Messenger Wind Juppos stimulator, and you can able to see this little white spot here. Yeah, that's the ray craters. Yeah, ray crater, and also a lighter region. And if you look carefully, probably you can barely make it out. But the next image is even better. This is like maybe four days later, and you get able to see from crescent to a little past more than half. Mercury moved very quickly, and you can see the phase changes one day to the next. That's how quickly Mercury moves. And of course, now some of the features thought to visible to, of course, Mercury's surface now, at least from half to Gibbous, it exposes most of the surface, and during the right conditions, you can able to detect some of the details. These are ray craters here, and this is one right here. That's the faint one here. Even though it doesn't show up too well on the Messenger imaging, because it depends on the face angle. And this time it would show a lot brighter than it appears in the Messenger image. There's several details here, a few of them here, this mark here, it's right here, and this is another ray crater right there, and right there. And of course, I have some identification to show you. And again, 3 days later, on June 29th, now you see it's getting gibbous, getting fatter, and exposing much of the surface. And some of the detail now it came into view, and you can able to spot it here. One right here, there's another one right there, this one here, there's another ray crater, and this so forth. Okay, now we have another observer, Gregory Shannon of Lombo Key, Florida. He became very interested in imaging Mercury, and I helped him in a way to process some of the images and give him some advice and all. And he came up pretty good. I mean, so this is he took images of Mercury before, like in the past year, but I believe this is his best work. I have this one, but I have another one too. And this was taken June 29th. And now we're able to detect faintly detailed on the surface compared with this Messenger image and compared to his image. So, here to provide some information like how bright it was, the thick diameter, the phase, how high Mercury was in imaging, and the scene condition, and so forth. But these are the information that you needed to, to try good information how the image was taken. And of course, you use long pass red filter, 685 nanometers, beta fatter long pass filter. So that's more concentration on infrared to give help to give more. But this is absolutely fun. This is a great way to start, and hopefully he will continue. But I have more images coming up. This is also June 30th, and you're able to see some of the details much better. See, the more surface exposed, the more details you will see. But on the downside about it, that mercury getting smaller and smaller until it's no longer visible. But again, you'll be able to see some of the features here, ray crate, all the ray craters here. They are absolutely phenomenal. And they're very easily photographed, doing imaging photograph using filter to make sure the conditions is right. And don't forget, all the pictures that you see, all were taken in daylight when mercury was close to the meridian. Now, how I find mercury? Well, I found mercury when close to the meridian. I used Venus as a guide. Venus was nearby. I set up, I pointed Venus first, and I set up the coordination, right descension and declination. And also I get the location, the coordination for Mercury. And that will help me determine how far to have to swing the telescope over to Mercury where it should be. And believe it or not, in low power I found it within a minute. Now, without Venus, it probably would take a little longer to find it in daylight. Now, unfortunately, I don't have a good eastern horizon. So I have to wait, like any planet that's on the eastern horizon, I have to wait for it to get high in the sky. And secondly, the telescope was in the shade out of the sunlight. So you got to be very carefully, make sure you don't get too close to the sun. So I explained that many times there. So this is just to give you an idea that, what can be done. Okay, this is another one, it's July 4th. And you can see this past week how good the image was. I never experienced such a good seeing condition all week long. I mean, that's pretty rare, especially around this area. And I had good weather and good seeing whole week, and that provided me to get good images of the number of sequences each day. Now, this is all the white spots, the ray craters you can match up here. Gregory Channel, July 4th. This is probably the best image I ever seen. Look, all this details here. This is what I process because I just process the way like it's my image and get to help out the detail as much as possible without over processing. Well, he did very well imaging, and I did processing. And here's the messenger image, and it's a slightly blurred. You can see it's slightly blurred. So in order to be equivalent to the resolution of an amateur telescope, and if you follow here some of the ray craters here, you see one here, this there, and some of the details right here, ray craters right here, and the one right there, here, all match. It's very consistent one another. This is the best way to identify whether or not, make sure it's not an artifact or the real feature. And this is a way to identify here. And also the next image, and I'm able to identify his image, what features that he captured. Like for example, that number one, this is water ray craters, Luga Plantemia, which is located right here. And the second one is another ray crater, which is Bartok ray crater, and which is right here, you can see here. And number three is Degas ray craters, which is number 3 up here, it's marked there. And 4, I don't know how to pronounce its name, but it's another crater there, but it got a very, very dark crater floor. And it's visible at the black spot right over here, the messenger, and you picked up very well here. And number 5 is Buda Planitia. It's not a ray crater, but it's some kind of dark feature, a beetle feature, and you picked up very well. And the next image July 4th, we have my image and his image taken at the same morning. So this is nearly simultaneous observation. It's only a couple hours apart. And if you follow closely, it's very nearly identical with one another. And here's some of the ray craters there. There's one right there, and this one here. So we will mainly capture the same feature. One right there, this one here, another one there, and this one here. So this is my image and this is image. It's really consistent with one another, and this is how the best way to identify, what we see in order to confirm, yes, it's the real feature and all, and also compare with WinJupyter's simulator help to identify whether it's real or not. So this is pretty good work here. But, okay. Also, I create a 7-image animation. You can see it from Princeton to Gibbous. This is one of the best work here also. And I do plan to write another paper for the ALPO journal on this part of the surface. The one is public now, that's on the other side of the surface. So it's two different parts of the surface show different features. So I'm planning to write this, and you can see here, if you look carefully at the animation, you can see the features moving from left to right. And you can see it's not actually the rotation of Mercury, but it's the orbital Mercury, it's orbital Mercury going around the sun. So this is one of, I'm pretty proud of this, and this is one of the best work I did here to present the Mercury studies. Okay, now the final images, the ALPO Mercury session will continue to collect observation. How many more ejected ray craters worldwide can be seen in amateur telescope? Well, I mean, it's quite few that I've seen it. So what are the brightest ray craters visible in certain longitude? And so far, the two brightest ray craters are Allerton and Debussy. There are more. And Kuiper crater, which is the brightest on this, as you see on my previous images back in November 2020, is the brightest, but it depends on the solar angle I've seen from Earth, whether it's high noon or very sun shallow, more shallow effect or something like that. So as it moves around, you can see the brightness variation. And still more work needs to be done. All right, again, keep observing Mercury, folks. If you ever plan to travel in the near future, you want to go someplace really hot, so go to the travel agency. If they plant Mercury, go. Okay, and I'd certainly like to go there. So, all right, that's it, folks.
Thank you very much, Frank. We're going to go on break now, but I want to remind everybody, Frank needs all the help he can get from all of you who can find any time to throw a couple of good quality Mercury observations this way.
Yeah.
Tim, your turn.
Yeah, and I just want to say that we have one question in the chat from Kim.
Kim, yes.
And her question, where is it? Where did it go? There it is. Hang on.
Is that a chat form or?
Yeah, she said she wanted to know what size telescope is being used to view Mercury. What's the minimum size, would you say?
Okay, you don't need a large telescope to observe Mercury, because if you have a large telescope, then the portability would be very difficult, and it just, then you magnify the turbulence and all. But in order to see the Mercury, just the minimum telescope is possible, maybe a 4-inch or a 6-inch, you can be able to see the face of Mercury like you see on the moon. I've seen Mercury through the 8-inch, 10-inch telescope, like 10-inch telescope like I have now. You get phenomenal. If you look at the right time, you get fascinating view. I mean, I say to myself, when I had a good view last June, I'm under the high power. It looked like you're looking at Venus in low power. It's such a high power. Using the filter, maybe the orange filter, helped to darken the background a little bit to create the contrast. I said to myself, oh man, this is absolutely sunny. I had never seen Mercury so clear before. And I try to go see if I can make out any details on it, but it's a little difficult because there's some turbulence in the atmosphere and it just popping in and out. But with the CTG to just bring out. But really, any kind of telescope, dude. You don't need a large telescope because Mercury is bright enough, and of course you magnify the atmospheric turbulence, and you don't want that. So you don't want to go too small, otherwise, maybe you can barely make out the face. But I would say maybe like 6 inches, at least 6 inches, 8 inches telescope probably would do a good job.
Great.
Thank
All
you.
right. Thanks, Frank.
Frank or Tim, what time do you want to pick up this afternoon?
We were supposed to start again at 20 minutes after the hour. Let's make it 30 minutes after the hour. Anybody having issues with that, or does that sound good?
3:30? No,
3:30. We'll pick up at 3:30, everybody.
Yep.
And our speaker will be Richard Schmoody.
Sounds good.
Okay. All right. Hey, Gregory? You can hear me? I think you're on mute.
Yeah.
Yeah, how are you?
Good. Oh, thanks for showing my observations.
Yeah. Fascinating work, really fascinating. That's the way to do it. I mean, it took me a long time to be where I am now, and it's just absolutely stunning. I hope you continue, like maybe.
Oh yeah, I will. I
Yeah.
will. Always email me and tell me Mercury's good now. Call to duty, like I say.
Right. Yeah. Yeah. No, I find it hard to believe that at little 20. I mentioned this before. About 20 years ago, this is something that cannot be done. Even a professional astronomer, they're struggling, to get an image like you see now.
Yeah,
but they just couldn't do it at that time.
I know. Well, the thing is, I have a 10-inch. It's a go-to telescope, so
right. Yeah.
I don't have to. Like you do, I guess you don't have the go-to, but I mean the ZWO cameras have such high frame rates. I mean,
right,
I was getting like 400 to 600 frames per second on Mercury. I was getting so many, and I just stacked the top 10%, of those. And that's what, and the scene was very good on July 4th. It's the best.
I know. I could tell that. Yeah.
And I imaged the other planets too. I think I imaged Jupiter that day, Mars, Venus. I imaged all of them except for Saturn.
Yeah, I know. They all on one side. Yeah. I find it amazing that some of them past astronomers like Chuck Dorelli, I mentioned, Christopher Lowell, and all. They've seen Mercury all their life. They study Mercury all their life, but they never come up with any conclusion of what they've seen. They cannot understand what they've seen. I mean, I wish they were alive today to see this. I mean, this is absolute,
I know. It's a technology. I wish that quick map Mercury had the central meridian, because it's hard to tell what face I'm seeing. It has longitude and latitude of the feature. It's kind of useless. If you knew the central meridian, you could go right to that, and then you can compare the
it doesn't say the day of your observing Mercury, observing will be visible on this portion here. No, when Jupiter's.
Yeah, I know. I use that. I use that. But when Jupiter's doesn't have everything identified either. It just shows the.
No, that's the opposite. The one that the quick map, they identify what features you're looking at. Whether the ray craters or white patch or whatever.
Yeah, but it's hard to know what face you're looking at on that. That's the problem, But it's great. So when's the next good apparition?
In October in the morning.
October in the morning.
In the morning, I always get good images. I very rarely, In the evening apparition, I get good image, very rarely, maybe once every 2 years, I would say.
Oh, really?
And
Yeah.
yeah, I can never produce any image, quality image like you see on the screen for the evening apparition.
Yeah, because the evening, it's going down and it's getting into thicker parts of the atmosphere, and the scintillation gets worse. Whereas it's just the opposite in the morning. It's getting higher and higher, and the scintillation's getting better, getting less and less.
Well, no, yeah, even
Plus
though
the daylight helps too.
Yeah, like in the morning apparition, even during the daylight, Mercury's still bright enough because they have a high surface of brightness. So it takes up the magnification really well. I mean, that's why it's easy to do it. And that's the best way you can see. I mean, if you want to see just a face and all, I'm pretty sure you can see whatever Mercury visible in the naked eye and all. But if you want to see the detail, if you want to do more than that, it has to be done in daylight when it's high in the sky.
Yeah, I know.
There's no way out.
But I like a good challenge, you know.
Yeah.
Like Mars is easy, Jupiter's easy, Saturn's easy.
Right, exactly.
You know, the clouds of Venus are a challenge too. I like that.
That's half and half. Yeah.
But that's the most challenging of all. You know, I see Uranus and Neptune, they don't show very much, you know. But Mercury's kind of neat. It's really, I never knew you could actually see the surface. And that Astra image, Astra surfaces, and
Astra surface.
Nobody knows about that either.
It's just fairly new. I mean, it's not too many people have that, but I find it very great. I find it great. Not only
next presentation, you should mention that program, how you get some of the, like how you process.
Well, that was a different kind of talk I would do.
Maybe next year do that, show how you actually process a Mercury image using the Astra surface. I think everyone will be shocked to know that even exists.
Yeah.
Everyone uses.
Well, you know, I only have like 20 minutes, so I can't go.
Yeah, I know.
But if it would be in person, like I always intended now for meeting in person, probably I would do that. Yeah, because that give you more time. So,
that's cool.
Yeah, so.
Well, where do you meet in person? What state? I mean.
What?
Before, where did you meet when you met?
Oh, Georgia.
Oh, Georgia. Okay.
Yeah, Georgia.
Yeah, I like the online because you know you can be in your own home and.
Yeah.
You know.
That was the last. This is the third year we have a visual meeting online. The last time we got together was 2019 in Georgia.
Yeah.
Which I went there. In Barnesville, Gordon College. That's where Richard Smootey located.
Yeah.
That's where,
The only good thing that ever happened with this COVID pandemic was everyone discovered Zoom. You know?
Yeah.
It was always there, but nobody used it. But no, necessity's the mother of invention. So you during the great shutdown, you had to communicate. So this is the way people did it. And, you know, people ended up getting used to it and actually like it. And a lot of our astronomy clubs are getting speakers from all over the country too. You know, because of that. So it's
well, neat. Our local astronomy club, Astronomical Society of Long Island. We have speakers from all over the place now. And visual meeting. Very rarely now. I usually give a talk too, but now we have other chance for people to give a talk and from far away. Rick Hill, he was here. He gave a talk. He gave a talk to the astronomy club. My friend Rick Hill.
Yeah, I looked up Holtzville, New York. That's in Long Island, huh?
Central Long Island.
Yeah, I have cousins that live in Great Neck.
Oh, okay, yeah, it's in Nassau County.
Yeah, Nassau County. That's not that's Long Island too. Yeah.
Yeah. That's the beginning of Nassau County after New York City.
Yeah. So that was kind of neat. It's a nice area. Yeah.
I think so. Yes. You ever been up to New York? You ever been to New York?
Yeah. I'm originally from Rhode Island. I was.
Rhode Island. Okay.
Yeah, I got married in 1990 and relocated to Florida.
Oh, okay.
Yeah, so I grew up I was born in Providence, lived and worked most of my life. Yeah, so I've been to New York because, you know, my cousins are Great Neck. So saw the Museum of Natural History and Statue of Liberty and all that stuff.
Yeah, right. Yeah.
When I was a kid, so.
Yeah, now, like I mentioned, my sister-in-law, my wife's sister, has a house in Lombard Key, Florida. It's not too
Yeah.
far away from you.
Yeah, I know.
Yeah,
I know.
not
Well,
too far
next
away,
time you're
yeah.
down,
Yeah, well, they're up
let me
here
know.
now for the summer.
Oh, they're
Yeah,
up here. Yeah.
Yeah, yeah, so, yeah. I
Yeah,
was,
it's very hot down here.
you know, my, they invite us, me, my wife, and my daughter down there. And I didn't go because I had to work, but my wife and my daughter went down there just before COVID started in March
Oh.
2020. And they spent a week down there. Yeah. Yeah, the
Well,
thing's
next
beautiful.
time, just before you come, contact me. We'll get
Yeah.
together.
Yeah. Well, I was supposed to go, and as far as I know, I go the following year, but we don't know how bad the COVID would be. But
Yeah,
then I never gone down there.
I always put Sarasota because no one knows what Lombard Key is. They think Lombard
Yes.
Key, it sounds
Yeah.
like Key
When
West,
when they fly
like
down
your
there,
Florida
they
Keys, you know.
Yeah.
And
Yeah.
so I just say, because I'm just 5 miles from the mainland, you know.
Right,
I'm
yeah.
very close, so
Yeah.
I just say Sarasota.
Yeah, when they take the plane down there, they land in Sarasota.
They say land in Sarasota.
Yeah.
Yeah, there's an airport in Sarasota. Yeah.
Yeah.
So that's why I put Sarasota down, you know. If you
Right,
put
yeah.
Lombard Key, everyone's gonna think the Keys, you know.
No, to be honest, I never heard it too until my sister-in-law.
Yeah, no, yeah.
No. Oh, where's that is? Oh, it's on the Gulf side, near Sarasota. Oh, okay.
Yeah.
Now I know where it is.
Yeah. This is a great conference. This is really good.
Yeah. Now, I'm just wondering in the future whether when we meet in person, I just wonder. I'm going to find out whether it's going to be a hybrid conference, whether it's going to be online and visually and meeting in person at the same
Yeah,
time.
it should be a hybrid, I think, you know, because I would like it on. If you guys want to get together in a salon and all that,
Yeah.
but, you know, put it on YouTube and stuff or Zoom, and that way people.
I'm going to mention that. It's a good idea if you're going to have that in the future.
If you need a small fee, that's fine. You know what I mean? Just to log in, you know, to
Right,
pay for hotel fees and all that. That's no big deal, you know. I'm gonna take a short break. I'll be back.
Yeah, me too. Okay, I see you later. Okay, all right.
Okay, all right. Great talking with you, Frank.
Yes, okay, great. We're going to talk many more yet. All right.
Testing.
Hey, Richard.
Yes.
Okay, when you start at 3:30, you'll have 25 minutes, so keep tabs on your time.
Okay. Okay.
All right, looking at my clock, it is 30 minutes past the hour. So, Ken, hand it over to you.
Okay. All right, it's my pleasure to once more introduce Richard Schmoody of Barnesville, Georgia, southwest of Atlanta, where he, let's see, one more time here, he got his PhD in physical chemistry at Texas A&M in 1994. He is currently a professor of chemistry at Gordon State College in Barnesville. He is the coordinator of the remote planets section, of which he's going to talk about now. He's also coordinator of the Jupiter section, and he's also assistant coordinator in the Mars section for photometry. Now, regarding the remote planets, he's going to talk about the remote planets during 2020 and 2021. And just a brief abstract on this is that 13 individuals submitted observations of Uranus and Neptune during 20 and 2021 during that apparition. Mr. Fox made over 120 B, V, and U filter brightness measurements of Uranus and Neptune. The normalized magnitudes of Uranus and Neptune are like those in the previous apparition, so not much change. The main albedo feature on Uranus is the bright north polar hood, and this is obvious in near infrared light, but not so much in visible light. Pellier reports R and I filter albedos for the north polar hood and the disk of Uranus, and the albedo difference is greatest in the I filter and smallest in the B filter. You all got that? There's a pop quiz later. And once more, this is one of the more, I don't want to say neglected, but this section could use a lot more support, just like our Mercury section. So those of you out there who can help with getting apparition reports to Rich Schmoody, we would really appreciate it. So at this time, I'm going to turn it over to Rich. Take it away, Richard.
Okay, thank you, Ken. Okay, today I want to talk about the remote planets, and by remote planets, I mean Uranus and Neptune, although I would love to get some Pluto observations too. And how many of you do not have a go-to telescope? Raise your hand. Do not. All right, I want to say something very important before I get started in my talk. As Frank alluded to in his last talk, Mercury can be difficult to find. Uranus and Neptune also can be difficult to find. Now, pop quiz. Here is your pop quiz. What am I holding here? Somebody answer orally.
Binoculars.
Binoculars. Yes. I cannot overemphasize the importance of binoculars, particularly when I'm just starting out. Maybe, I don't know, last year I started observing Neptune in June. Of course, Neptune changes position. It's not like observing variable stars where you kind of get used to the star field. Neptune moves, Uranus moves, Mercury moves even faster. You need binoculars and a good star chart to find these planets. And actually, I use two different star charts. I use the AAVSO finder chart. That gives a big field of view. And then I use the Uranometria. It was the 3-volume set. I forgot what the name of it is now. That kind of zooms in a little bit. Now, of course, you've also got Sky and Telescope. I think they publish finder charts for Uranus, Neptune. I believe the British Astronomical Association does as well. So anyway, get you a good finder chart, but most importantly, you need what to find Uranus and Neptune. I can't hear you. What do you need? I can't hear you.
Binoculars.
Binoculars. Very good. And so anyway, well, let me go on ahead and get started. In the next slide, I'm just going to give an overview of the talk. I want to make a few introductory remarks. Of course, I already made my big introductory remark right here with the binoculars. And then I want to talk about photoelectric photometry results. And then I want to talk about some disk features. And of course, this is also very important for the other planets. We can actually now get reflectivity measurements of individual features on the disk. For example, Frank talked about several rayed craters. How does the brightness of these rayed craters change as Mercury rotates? This is something, Frank, I'm hoping you can think about, when you do your Mercury work. And of course, I noticed one of the imagers was on there too. Shanos, I believe was the last name. Think about that. And of course, we've already got the whole disk brightness measurements of Mercury, and now we need to getting the brightness of individual features. But of course, Christophe Pellier has already done this with Uranus. So I'm going to, I've already discussed that in my apparition report. So anyway, so again, I'm going to make some introductory remarks, talk about photometry, disk features, and then wrap up with some conclusions. And I see I got an extra O there, but anyway. Okay, next slide. All right, first off, unlike Mercury or Mars, Uranus and Neptune are quite different. Uranus is tipped on its side, axial tilt of 98 degrees, which means it goes through extreme seasons. Neptune's axis is tilted similarly to the Earth. But look at this here. The orbital period is 84 years for Uranus. That means one season is 21 years long. And Neptune, a season is about 41 years long. Okay, so again,
You're muted.
You're muted, Richard.
Okay.
Richard, okay.
I must have accidentally done that. Okay, I'm sorry. But anyway, if you're going to study Uranus and Neptune, you probably need to start young. And of course, you can watch it change as you age. Okay. All right. So that's a little bit about Uranus and Neptune. And I, back in 1990, I was appointed I guess the acting coordinator of Uranus and Neptune. And I knew one thing I could do with the limited equipment I had was photoelectric photometry. So I went and purchased a single channel photometer. Actually, a friend of mine, Bill Winkler, showed me his that he had purchased a few years earlier. And so I really have to owe a lot to him. But anyway, that's where I got it started. I started taking my first brightness measurements in 1991, which is just, I guess it's about 31 years ago. All right, so let's now talk a little bit about photoelectric photometry. In the next slide. Basically what this is, photometry is a measurement of brightness. Photoelectric photometry is the use of an instrument to measure brightness. Of course, instruments can oftentimes get very accurate brightness measurements. However, Uranus, like all the planets, reflect light. That means the brightness of, say, Uranus or Mars is going to depend not only on the distance between the observer and the planet, but also the planet to sun distance. You got two distances to worry about. So any change, so what you do is to get rid of the distance effect by calculating what's called a normalized magnitude. This is abbreviated as V1 comma A or V1 comma alpha. And this is a brightness after corrected for distance. So in other words, any change in V1A is going to be due to changes on the planet, not due to changing distances. Now, Mercury is an interesting exception because in the H filter, which is in the near infrared, actually there are some thermal effects. And I'm looking forward to Frank's next talk. I mean, at least I think that's Frank's talk about, that's not a comet, but we'll see. So like I said, any change in the V1 comma A is caused by disk reflectivity. Okay. Right now, members of the ALPO remote planet section have been collecting brightness measurements of Mercury since 1991. How many years ago was that? I can't hear you.
Whole bunch.
A whole
31.
bunch. 31. Very good. Very good. So like I said, it's you got to be really, really, really patient with Uranus and Neptune, unlike Mercury, which can change phase in 1 or 2 days, as Frank showed in his talk. So in the next slide, I'm going to show you a graph. Okay, now on the vertical axis, I have the V1 comma A brightness of Uranus in stellar magnitudes. And of course, a stellar magnitude can be converted to a unit like energy per square meter per unit time. And then on the horizontal axis, I have the year going back to 1988 all the way up to, oh, actually, I think it got late 2021 here. All right, so what do we see here? Well, we see a gradual dimming trend until we get to about the year 2009 or 2008. Now, what happened in late 2007? Anyone with Uranus?
We have the edge on view.
What?
We have an edge on view.
Yeah, essentially edge on view.
Edge on pentation, yes.
You know, we were, Uranus was at equinox. The equator was facing us. Okay. Now, what's going to happen between 2007 and 2030, by the way, that's only 8 years from now, is in 2030, Uranus is going to be at solstice. In other words, the pole is going to be facing us or nearly facing us. And what trend do you see happening between, about 2010 and 2021, late 2021? What's happening to the data? I can't hear you.
Getting brighter.
Okay, very good. It's getting brighter. Remember, the more negative the normalized magnitude is, the brighter it is. Now, this is very interesting. Now, we know that Uranus is slightly polar flattened, not by much. It's not quite a circle. So when the North Polar region faces it, Mercury is more of a circle, but when the equator faces it, it's a little oblong or elliptical. But that's only about 0.02 magnitude. Okay, and again, we're looking already at 1/10 of a magnitude here. And what is happening is there's some interesting things that seem to be taking place. And one possibility is, of course, this bright North Polar hood forms, but it's not really bright in visible light. It's bright in infrared. Okay, of course, you see the Hubble Space Telescope images showing the bright North Polar hood. That's infrared, people, not visible light. Okay, so some interesting things are going on here. We don't quite know why it's brightening so much. One possibility is you may be getting an effect due to the emission angle getting smaller. Of course, that's an angle that's defined in photometry. I don't have time to go into that, but anyway, stay tuned. But some interesting things are happening here with Uranus over the last few years. Now let's just see what happens. Interestingly enough, they measured the brightness of Uranus back in the 1930s. I'm not sure about the calibration techniques, but the brightness was close to minus 7.3. And of course, that would be similar to what we're going to have in 2030. So let's just see. Some very well-known scientists, I believe was Stebbins was one of them, very good photometrist from the 1930s. Right, so that is Uranus. Now, what is happening on Neptune? Neptune's a little more complicated. Remember, how long is a season on Neptune? I need an answer orally. How long is one season on Neptune?
184 years.
Okay, that's a whole year, roughly.
41.
41 years, right. That's about half of a human lifetime, roughly, I guess. All right, so here we have the V1, A value for Neptune, again in stellar magnitudes. And we're starting back here, 1991. Now, between 1991 and, the early 21st century, Neptune brightened. Okay. In 2005, Neptune reached solstice. Okay. Now, it is sort of stuck here at this high level of brightness. It might start to be going down here. Stay tuned. Let's see what it does in 2022, later this year. But it looks like Neptune might be starting to try to dim, although it tried to do that a few years ago and just brighten back up. So again, it'll be interesting to see what Neptune does. There seems to be some interesting processes going on there. Of course, amateurs did image some bright spots on Neptune, maybe not as many though as in previous years. So Neptune may be going through some changes itself. But again, the only way to know is to take a look and take some pictures. All right, so that is Neptune's reflectivity. Now, some conclusions. First off, Uranus is dimmer at equinox than near solstice. And of course, even Wesley Lockwood and co-workers out at Lowell Observatory, they've been measuring the brightness of Uranus, believe it or not, since 1950. So that's roughly 72 years. We have almost a full year of Uranus data. And so it's interesting. Uranus does go through a seasonal brightening trend. Neptune is a little more complicated, but it does appear Neptune is brightest near solstice. All right. Now, the next slide shows some pictures from late 2021. Actually, one of them from 2022. Again, you see a big bright area near the bottom. Of course, south is at the top. This has been imaged for several years now, since I believe at least 2011. Very quick quiz here. Give you an answer orally. What wavelength of light do you think this picture was taken in? Don't be deceived by the color.
Infrared.
Exactly. It's infrared. It's not green light. I know it looks green. That's the key. Now, next quiz question. Can our eyes see infrared light, say at a wavelength of 1 micron?
No.
No, they cannot. So again, folks, when you go to the telescope, don't expect to look for this big bright area on Uranus. You probably won't see it. If you do, really let us know, so that I can set on email and see if we can confirm it. Neptune, similar. Although I will tell you, Neptune is a lot harder to identify in the telescope just because it's smaller, and the seeing usually is about almost as big as Neptune, about 2 arc seconds. So, but again, you can see in sort of the upper right portion of Neptune, you can see sort of a brightening there, possibly a polar hood there, or possibly just a bright spot on Neptune. Okay, taken by Villadrich. By the way, he took this picture at an elevation of like 2,900 meters on the French-Italian border, but on the French side. So again, very good facility he used. And I believe he used a 62 centimeter telescope, which is like 24 inches. Now, what I have been doing over the last decade has been measuring the size of the North Polar area. And I just carried out some measurements using the WinJupos. Very good software. You can use it for any planet, not just Jupiter. And this next slide shows a graph of the latitude of the North Polar cap edge. Again, this can only be seen really in near infrared light, plotted against the year. I do want to add one more point, and that is late 2021, it's dropped back to about 43 degrees. So this trend of getting smaller has reversed, and maybe this is just sort of one of those outlier points. I don't know, from late 2020. But anyway, North Polar cap has apparently more or less stayed near 43 degrees north. It did get apparently a little smaller in late 2021. But again, this has been a constant feature now for, I guess, 11 years, going back to late 2011. Now, interestingly enough, Christophe Pellier, and I talk about this in my 2021 report that hopefully will be published early next year. Christophe Pellier, what he has done is the following. He's actually done a couple of really great things. First off, he's able to take spectra and from that calculate a whole disk brightness measurement. But he's done something else. He's taken CCD images and he has measured the brightness of just the North Polar region of Uranus. And he's able to report reflectivities of just the North Polar region, the rest of the disk, and the whole disk. This is disk integrated photometry. This is in its infancy, and I really, really feel there's great potential in the ALPO to do more of this. Frank showed us some really great images of Mercury. The next step, I mean, I think, Frank, you've demonstrated we can get detail on Mercury. You've done that. That's great. And you and your observers, Shanos, I know, is one of them who's done really good work. The next step is now to go on ahead and get brightness measurements. So in conclusion, next slide. Next slide. Uranus and Neptune probably undergo seasonal brightness changes, and the North Polar hood on Uranus, I don't think it's shrinking. That's what I thought last year, but now it looks like it's sort of stable. So anyway, thank you for your attention.
Thank you, Richard.
You're welcome.
Thank you, Richard.
You're welcome, Ken. Hopefully I stayed in the time limit.
You did. We have a minute or two. We have a minute or two if there's a question. Oh, come on.
Any Pluto work being done?
I would love to see Pluto work being done. That's going to require a CCD camera. You know, amateurs can do it with as small as a 10-inch telescope. Frank Maleo has done some work in the past showing at least Pluto moving and also getting an approximate light curve. Frank was able to get an approximate light curve. But yes, there's nothing stopping you. I'm not going to stop you from getting it. I'd love to see some Pluto work. Yes, very good.
Yeah. One thing about that, I would recommend doing when Pluto reaches the stationary point, because that will keep in the CCD field a long period of time, and for numbers of weeks. I did that in 2014, if I remember correctly, and I have about 10 images of Pluto in the same field, and doing a retrograde, doing stationary point. That's when it was resumed easily motion after the retrograde motion. But it's very hard. I think that the very small brightness as Pluto rotated every 6 days, but it's very hard to confirm that. I mean, compared with other stars in the field, it seems like it varied maybe like 2/10 of a magnitude, something like that. But it's very hard to confirm that.
Yeah, it's about 0.2 magnitudes, but that's changing too.
Oh, yeah, but now it's a lot fainter because it's moving away from perihelion orbit now.
Here we have the two guys on both sides of the solar system, Frank Melillo and Richard Schmoody. Think about it.
Richard,
Yes.
doesn't changing the position of Charon, its moon, affect the photoelectric reading?
Yes, Charon is going to contribute roughly 10% to Pluto. I believe it's on the order of 10%, but Charon seems to be more uniform than Pluto. Pluto's the one that's changing. It's what's causing the brightness to change. And of course, we're over with the occultation. So Charon is not going to move in front of Pluto until, I think, the 22nd century.
Wow. Thank you, Richard.
You're welcome.
Richard. Okay,
Thank
at this
you.
time, we're going to jump back into the lunar side of things. I want to point out, for those of you who have your Zoom screen set to gallery, even though the picture isn't up, Chuck Wood, our featured speaker for the evening, our keynote speaker, is logged on. So we're on best behavior. And also, I want to
You're always on best behavior. This is Chuck, so I'm enjoying it. Thanks.
Good. I had a chance to meet Chuck a few years ago when I stopped off at his place in Wheeling, West Virginia. Where in the world would you think that such great work on astronomy comes out of Wheeling, West Virginia, but Chuck Wood does it. Also, I want to compliment the lunar section's assistant coordinator, Craig McDougall, on a great picture of him with his sax. So that's an astronomy oriented thing, I guess, maybe not.
And if you go back to a podcast that I had with Craig, he actually did a mini concert at the end of it as well. That was very enjoyable.
And I do drums. We got to get together.
There you go.
In my defense, I got a text and I didn't think you all wanted to see the top of my head while I was replying to it. So, but yeah, that's me playing in a cover band, playing, and they wanted a 60s theme. That was just after I got done doing the sax solo to the Rolling Stones' Brown Sugar.
There you go. Well, I do drums and we play the same stuff. At least it's not rap. Okay. Our next speaker, Alberto Daniel Annunziato, I hope I said it correctly, of Parana, Argentina. And Alberto is an amateur astronomer. He's an assistant coordinator in the lunar section of the, he's coordinator of the lunar section of the Liga Iberoamericana de Astronomía Iliada. And I assume that's an association in Argentina. And he reports regularly to David Teskey after his work is carried in the Lunar Observer since 2015. And let's see, he is going to talk about visual observations of the moon can still have value if they focus on the selection of the most important information previously determined by the theoretical conceptual framework and later confirmed by the photographic image. Okay, you got 25 minutes to fill us in there, Annunziato.
Okay.
Mr. Annunziato, take it away.
Okay, can you hear me well?
Yes.
Well, it's a huge honor to be here with the ALPO's friends. Allow me please to read my presentation so you better understand my English, my alien villain B movie from the 50s accent, English accent, no? I am more comfortable in reading, but I'm open to questions. I will share my screen. Can you see my presentation, my PowerPoint?
Yes.
Yes.
Okay. Well, Is visual observation of the moon still worthy? Well, a quick answer for the anxious like me wouldn't be a certain answer. Most likely, no, maybe yes, but in a very restricted field. The art of seeing, the practice of seeing, is an essential part of the observation. This practice has an antecedent, the set of prior knowledge that shapes the observation. I would like to share some reflections on visual observation after some years of practice, at times alternating it with photographic observation. My guide in this somewhat philosophical tour of our daily practice are these two books that refer to selenographic studies in the past, but are fundamental when we want to understand how we approach visual observation, at least lunar visual observation. From the first book, we took this table that perfectly represents the cognitive process through which visual observation was transformed into scientific knowledge in the times before photography. In this timeline, we see some milestones of selenography. Let's see how is the role of the conceptual framework, the previous conceptual framework in the observation. We might think that the first telescopic observation of the moon had no previous references, but this is not the case. Galileo Galilei observed the moon in 1609, seeking to confirm one of the two conflicting models on the lunar surface. Galileo hides the source, the philosophical source, to highlight the factual data, but the truth is that he seeks to confirm Plutarch's statements about the moon as another Earth. His drawings has the objective of showing that similarity between the moon and the Earth, rather than the cartographic veracity. Modern astronomy owes an unrecognized depth to Plutarch because it was a privileged source to the first visual observation of the moon. So Galileo's observation had a conceptual framework that allowed him to guide his observation, Plutarch's. The purpose of Galileo's drawing was not cartographic, was to show that the moon has a similar relief to the Earth. The history of post-Galileo selenography will be what Sheehan and Dobbs called the Great Race to Map the Moon. The objective was to map the complete near side, and the purpose was to locate the selenographic features in the map and not to show non-essential details. So these details were omitted in these grand maps. It is with von Schroeder's selenographic fragments that the detailed mapping of small areas begins to prevail. Unrecorded characteristics of lunar features began to be mapped. Rims and central peaks of craters, also the wrinkled ridges and rills. Before von Schroeder, these details were not recorded. Were not recorded because they were considered useless for the purpose of the great general maps, or were they not recorded because a semiotics, a taxonomy to guide the observation had not been discovered? Well, we don't know, but the fact is, since von Schroeder, each map, each observation adds new details that will allow the next observer an even more detailed observation. 1895, with Elger's The Moon, is the culmination of the collaborative effort of a community, an army of amateur selenographers, who repeatedly observed the same features, adding details, but limited by the ignorance of the lunar geology. But it is an interesting model for modern visual observation. Space probes in orbit and then on the surface provided the definitive understanding of the lunar geology. Subsequent observations built on what was discovered in the space race. The first use of a CCD astronomical camera was in 1976, but it was much later that its use became among amateur astronomers, especially in our century. So we can say that photographic observation is occupies a very limited space in this timeline. No, that is certainly a visual story more than photographic. Correct. With images as impressive as the examples we see from ALPO's friends, there seems to be little room left for visual observation. Has photographic observation prevailed over visual observation? Obviously, yes. Seeing these wonderful images and all the images that are reported to the lunar sections of ALPO. Going back to Manasek's frame, obviously crossing out field D, because we are not dealing with the problems of lunar cartography related to printing on paper, it is clear that observational biases are practically reduced to zero in photographic observation. There is no subjective interpretation prior to the production of the image, and in the production of the image, subjectivity is reduced to the stacking and processing of the image from the video. Visual observation, on the other hand, even today preserves the observational biases of the golden age of the selenography. Subjectivity in the interpretation of what is seen through the telescope, variation in the degree of visual acuity of the observer, the degree of prior knowledge that shapes the selection of the objective, the encyclopedia of data that the observer has in his brain, that condition is that determines the observation. The selection of the objective of the observation is primordial because the features that are considered essential are recorded. Not all the features, not all the characteristics we see on at the foot of the telescope, but only that features that are considered by the observer essential. That is why it is essential to be clear about what to record and how our observation selects information that could add something new. This was a clear factor in the history of selenography, in the history of visual selenography, that is absent in the photographic observation of the moon in general. An additional inconvenience is the degree of practice in the drawing and the explanation of what is noted. In photographic observation, the volume of information accessed by the observer at the moment of observation is less than that which the subsequent user, including the observer himself, can access. For example, by enlarging the image or playing with contrast. Visual observation, on the other hand, is closed. The observer has more information at the time of observation that is finally recorded on paper. What is not recorded is lost, which is why it has always been important how to deal with the selection of the information that the observer considers valuable and worth recording. With all these biases, is visual observation still valuable? Well, maybe. It would add telescope to the observation of people who doesn't have a camera in our countries, in our poor countries. This is a factor that is interesting. Also among the youth observers that don't have the money to buy a camera, and perhaps could add some information via visual observation. The next question is highly debatable. Are there aspects that the human eye can capture more sensitively than cameras? It's very unlikely. I can think in moon observation of degrees of brightness and shadows, perhaps. The eye-brain system can improve with training. This is important. Can improve with training and can improve with prior knowledge to the observation. The eye-brain system can improve to a greater extent than the camera software system. You can improve, I think, this this camera software system by a better processing of the image. The answer, in our view, lies in selectivity. Selectivity is a bias. Unrecorded information is lost, but the selectivity of the trained eye can be fundamental for modern visual observation, since it allows to focus on a certain feature, on a certain characteristic of a feature, while in photographic observation, the observer looks at the field of view of the capture software, in which there is less information than what arises after when you complete the final processing. Visual observation can still be valuable if it depends on photographic image. During a good part of the 20th century, visual observation refined the details, taking advantage of the cartographic precision of photography. Examples of visual observation using photographic images are the magnificent work of Johann Krieger and the United States Air Force lunar mapping for Apollo project prior to the lunar orbiter missions, which started from photography and ended visually. A new paradigm for visual observation could be based on the selectivity of the visual observer and the possibility of the photographic confirmation. Without photographic confirmation, visual observation is not valid today. Let's see a concrete example of the model we advocate for, a visual observation of the Luther crater north of Mare Serenitatis and the nearby wrinkled ridges. What can visual observation contribute? Not position accuracy, obviously, compare the image of the left to the Lunar Reconnaissance Orbiter quick map. What we selected at the moment of the observation are the brightest parts, which could provide data about the wrinkled ridge. No shadows observed, but we select two bright parts. One, the highest part of the segment north of Luther, which is the crest, the highest part of the wrinkled ridge. And two, and more interesting, what we think it was a segment of the wrinkled ridge south of Luther, which looked like a brighter band that seemed to literally run over the wrinkled ridge running north-south, crossing Luther. The brightness of this streak was visually very distinctive, brighter than a typical wrinkled ridge arch, and sharper than a typical bright ray. And there aren't any bright rays, craters nearby. So according to our conceptual framework, at the moment of the observation, our conceptual framework of what a wrinkled ridge should look like, this streak was anomalous. We seek to confirm the relevant data with the available information. Next step. The Lunar Reconnaissance Orbiter Quick Map doesn't appear to show any relief in the area. In the area south Luther. And its wrinkle rich map, its wrinkle rich catalog, doesn't indicate that there is a segment where we saw the bright streak, where we saw the streak marked with the number 2. We searched lunar atlases and found in Kwok CPAU's photographic lunar atlas for moon observers, a fascinating atlas. We find the stripe and its location. Pau's excellent image seems to indicate that our bright band is a wrinkle ridge because of its shadow casting relief, especially in the western segment. We published our observation in the December 2021 issue of the Lunar Observer, along with the Kwok image. Kwok, and this is also very interesting, Kwok read the text and wrote me an email commenting on it and attaching the following image. Kwok pointed out to me in that email that the two segments are different. The western one looks more like a wrinkle ridge, while the eastern one looks more like a depression in the terrain. Using the Lunar Reconnaissance Orbiter's Quick Map laser altimeter data, we confirm Kwok's opinion. The terrain has a pronounced slope on both sides, western side and eastern side, a pronounced slope to the south, and the western segment looks, if we see the relief, the graphic of the relief, the western segment looks like a wrinkle ridge, albeit very atypical, while the eastern segment doesn't look like a wrinkle ridge at all. Undoubtedly, a very particular relief, which deserves more images than we have been able to collect so far. So, see for yourself if it's not particular in this detail of Kwok CPAU image. The bright band overlaps the north-south wrinkle ridge that is, it seems clearly below like a bridge, no? As the bright streak is a bridge running over the wrinkle ridge, blocking out even the shadow. Photographic observation allows research like this, enlarging the image to the maximum, giving contrast, etc. A kind of, in quotes, a visual observation of photographic images. It remains for us to finish knowing what this relief is. Surely when we find more detailed images, we can elucidate this observational mystery. This is a true structure of what visually looks like a thin glowing line near the terminator. The visual observation selects, my visual observation selected that anomalous bright line that doesn't look like a wrinkle ridge, doesn't look like a bright ray. The visual observation selects that feature that we still seek to capture in photo. I mean the bright line. We have photos that shows the structure, not the bright line. I am personally observed visually at least 3 times this bright line, and the photograph confirms that there is a structure in that place. Perhaps a wrinkle ridge segment not registered, perhaps. So we have a visual observation with a previous theoretical framework that selects the essential information recorded. That is an anomalous detail that can add knowledge about an overlooked lunar feature. This information needs a confirmation on photographic images so we can reach a theoretical explanation that we still don't have in the case of this feature. In short, visual observation, whose contribution has been fundamental to understanding the moon, has today been overtaken by the photographic image, but its use may be still marginally valuable as an activity for nostalgics who find pleasure in looking and drawing. We are not the last lost patrol, but the vintage, the old-fashioned gentleman of the selenography. Well, thank you very much. Any questions?
This is Richard Schmoody. Very good talk, Alberto.
Thank you.
One thing to remember, you've got topography. That's going to affect, topography and lighting. But there's something else too, and that is you can have, I don't know, something like what I'm holding up here, this green stripe. As the emission angle changes, now so the angle the sunlight is hitting, even a flat surface, can brighten. And of course, we see this all the time when we drive at night. They put special stuff on the roads that light up, telling you the right-hand turn is here or whatever. So this would be, something to look at. I mean, and again, I'm getting into photometry, which is my field, but, this is something you all can do with CCD cameras, is you can actually measure the brightness of, say, Luther Crater or the Wrinkle Ridge nearby at different emission angles and actually get some photometry of just that little ridge. I mean, have you thought about doing that?
No, but it's interesting because we are in the process of knowing anything. My intention was to bring the results of what is this feature. What is this feature? But it remains unfinished. So I prefer to talk about the justification of visual observation. Yes, perhaps it's an art. This bridge, that overlap the wrinkle ridge. Perhaps it's an artifact. What is interesting is that is a rare, possibly a rare wrinkle ridge. But if it's wrinkle ridge, it is not cataloged as a wrinkle ridge. And for what I see in the Lunar Reconnaissance Orbiter Quick Map, it never happened to me that I saw a wrinkle ridge that is not in this catalog. So I think it's perhaps a feature that mimics a wrinkle ridge.
Could be. Very good. Thank you.
Tony, yes, there is a, Tony asked if I check the Lobate Scarp map. That is another layer, another catalog in the Lunar Reconnaissance Orbiter. Yes, I check. I'm not, I don't have much knowledge about Lobate Scarp, but it doesn't appear as a Lobate Scarp. I choose every layer as a monkey to ping. I click in every layer. I could find some miraculous solution, but no. My guess is that it's a feature that mimics a wrinkle ridge. Yes.
Alberta, this is Chuck Wood.
Hi, Chuck. It's a huge honor to know you.
I'm happy to meet you too. I like what your presentation was saying. I think the visual observing of the moon is very different from the the imaging, telescopic or spacecraft imaging. Every time I see a magnificent image, I feel a sense of what amazing technology that is. But when I'm visually observing, when I look through my little 5-inch Newtonian or 4-inch refractor, I feel a sense of awe. It's a human emotion that I get through looking through and just watching the shadows move over the course of an hour's observation, for example. That is so much more personally invigorating than looking at the best images, even though when I do research, it's almost always on the best images. But as you said with the wrinkle ridges, you can see things visually and they stimulate you to go and investigate them with the other data that we have available. And that's a great way to proceed. And I think also, I've been to Egypt and seen the pyramids. I've been to Argentina. I haven't been to Argentina, Brazil, and seen Rio de Janeiro and whatnot. And I did not make any discoveries in those places. I did, it's like observing the moon visually. You're there for the inspiration you get, I think, and for the self-learning. Every time I see the moon, I see something I hadn't noticed before. And so I just as I would love to go back to South America and Argentina and for the first time in various places, I want to do that for the understanding that I get of what's there, the culture in particular on Earth and the moon, not the culture yet. I thought by now we would have a culture on the moon, but not yet. So thank you for your talk. I enjoyed it.
Thank you very much.
Thank you. This is Julius. I really enjoyed the talk. It was great. One of the things I found out when I've been observing the moon is to use a binocular eyepiece. It gives it sort of a 3D effect. It really is great. Works beautifully. Of course, you have to buy 2 identical eyepieces, but that's okay. I enjoy doing that. I do almost all my observing with binocular eyepieces.
Yes.
Yeah, I one time took out my 5-inch ALPO refractor and put a 3.7 FOS eyepiece on. My wife has no interest in astronomy, but she looked through the telescope at the moon with that eyepiece and she was amazed. So, I mean, something like that. I mean, it's like you're looking at the moon and you're just a couple of thousand miles above the surface. I mean, you just don't get that same feeling with a photographic image.
Agreed.
Yeah.
Agreed. Thank you, Alberto. Thank you.
Thank you very much.
Thank you. And I hope you bear the winter. You're having winter down there. We're having hot summer up here.
But we have a hot weather, even in winter, and these days.
Okie dokie. Okay. It is my pleasure to once more introduce Mr. Malalilo of Long Island. And this afternoon, he's going to do a comet talk. So Carl's going to have a good talk with Frank afterwards. The topic of Frank's talk is imaging Mercury. What's this? It's called That's Not a Comet. Imaging Mercury with a sodium filter opens up a new role in amateur astronomy. So Frank, you've got 25 minutes. Use them wisely.
Hi, can everybody hear me and see the screen?
Yes.
Okay, Here we go again. My second talk. Just briefly, if you remember my first talk, just a short moment ago, what's up with Mercury 2022? It was just a general aspect about observing and any news throughout the year or imaging and all. So this talk, it's a little more specifically about Mercury. The title of the talk is That's Not a Comet. Okay, well, let me moving on to explain about it. Okay, and okay, all right. Certainly, this is not a comet, but this is one classic car. This is the 1963 Mercury Comet convertible. I'm pretty sure you like to get a hand on this car or drive around and all. That's a truly classic car. If I remember correctly, when I was a kid living in my parents' block, I believe one of my neighbors has a Mercury Comet, but I'm not sure what color it was or what year it was, but I didn't remember the name. So that's really a remarkable one true classic car. But anyway, moving along, this is actually a comet. Everybody remember, I'm pretty sure many of you remember that 25 years ago, we have a comet Hale-Bopp grace our spring sky after sunset and the evening sky. This is one of the bright comet in many, many years. I think it was the brightest comet since Comet West back in 1976, and it was visible easily right at the sunset at minus one magnitude, something like that. And spectacular tail, dust tail, iron tail, and so forth. And a year before that, 1996, we have Comet Hayasatake. So this is just a phenomenon now. And also just as recently, 2 years ago, we have Comet Neowise. And it's not as spectacular as Comet Hale-Bopp, but it was probably the brightest comet since Hale-Bopp. It was visible briefly before sunrise, and then it was visible in the evening sky. So we have both comets in the morning and the evening, just the number, just like in 2 days. You know? So this is my picture that I image. This is a comet that will look like with a tail or something like that, and a coma and so forth. Yeah. All right, the next picture. You see it's another comet there. And probably right after sunset, you probably see this picture. Then you go out with a pair of binoculars or a telescope, and right after sunset, you're trying to see the comet. There's nothing there. But you see Mercury there, right? All right, well, actually, is it the comet Mercury? Yeah, the Mercury sodium tail is photoed by an amateur. This was taken by Andrea Alessandrina, just one Italian astronomer. Was able to photograph the sodium tail, Mercury sodium tail. This is one of the image that he took. But I'd like to point out a few things here. One of my friend of mine from Long Island, he also became an ALPO member, Steve Bellavia. He imaged Mercury sodium tail with a sodium filter, which I would talk about momentarily. He used a very simple technique, a camera, a digital camera on a tripod, and used a time exposure, and you employ the filter, sodium filter. And at that time, the nearby crescent moon was there, and his Mercury right there too. But a close-up with a little processing, and you can able to make out the tail there. Yeah. This is very spectacular. It's right after sunset. Mercury was in the evening sky at that time in May 13 of 2021, which was right after sunset. And one of the favorable evening apparitions, so you can see Mercury clearly, and also you can see Mercury a little bit when the sky gets darker. So this is one spectacular picture. This was probably it was issued in ALPO magazine journal last year. It's a several more picture taken by the same person, Steve Bellavia, on Long Island. Last April 24th, he hit Mercury, and it's a tail. I mean, if you don't know it's Mercury, right away you assume it's a tail there. And this is probably the tail, the sodium tail is probably extended maybe about a ½ degree. Something it's not very long. I mean, don't forget Mercury is very far away from us, and the tail it depends on the angle. This would take it near the greatest locations, so you're looking at the right angle from the sun, Mercury, and the Earth, right angle, so you can see a maximum length of the tail of the sodium tail. So it's about a half a degree, maybe a 3/4 degree, something like that. Here's another photograph taken by John Vandral in Massachusetts. Probably many of you familiar with him with his mercury work that he did past 5-10 years ago. And this time you have the Pleiades, star clusters right here, and nearby Mercury, and here's the tail there. This is really, really nice. Yeah, black and white photograph because to get the maximum contrast. Here's the close-up picture of the tail. This is spectacular. So you got the spike here, and this is really bad. Mercury was pretty high above the southern horizon. At the same time, the sky get dark in the background. So you get able to image Mercury when the sky is a little darker before Mercury sets. So that's when you get the maximum length of the tail at the time. Also, it depends on the angle. If it's near superior conjunction, the tail will be behind Mercury. If it's inferior conjunction, and the Mercury tail, the Sonic tail will be in front of you. So you don't get really a long tail. Only near the greatest elongation. So now what I'm talking about when talk about this one here. This is one German amateur astronomer, Sebastian Vollmer. He's a German amateur astronomer, and he took a spectacular picture. It certainly looked like a comet, no doubt about that. If you don't know anything about it, or if you don't know this Mercury, and also I have the Pleiades star cluster. But don't forget that this is not actually one photograph. This is two photographs together. The image Mercury with the sodium tail with the filter, and then you took image of the Pleiades another time, and just combined two together. This is actually distant from Mercury to the Pleiades, but they were taken at two different times. But let me see if the next one. He showed also a very short video of how he took the image of the Mercury sodium tail. Hopefully, this will work. Let me see. Yeah, it does. Okay. All right, it's a short.
You gotta click on it, Frank. You gotta click on it, Frank. We're not seeing it, Frank.
If it pulls up a different screen for you to watch it in, Frank, you're gonna have to share that particular screen.
All right. All right. I'm sorry. This is Oh no. I'm sorry. I get this Oh, okay. Sorry about that. All right. Oh, okay. How do you get back to it? Okay. All right. I'm sorry. Sorry about that. Oh, okay, all right. Okay. Hmm.
You had it.
Yeah. How do you get it back? Oh. Well, sorry about that.
Just put up the link then and we can
Okay.
look at it. Put up the link and we can look at it later.
That's it. Blocking. Okay. Okay. All right.
Just show the slide with the link and we'll copy it.
Yeah. Okay. Okay. All right. That's it. Sorry about that. So, yeah, he sent me the images of the video, and hopefully I can play. So
Can you go back to the link? Can you go back to the link so we can copy it?
Okay.
Give us a second to copy that.
Oh yeah. Okay. Oh. Okay. I'm gonna to post it on a chat.
Everybody copied it?
Okay, yes.
It's in the
hopefully we
chat
can
now.
copy it. Yes. Okay,
Okay.
I'll put it in the chat. Okay. All right. So I apologize for the different language, the German language. So, but they have English subtitles. So to give you an idea, there's what a phenomenal work that he did from the Mount in Canary Island. The image of the sodium. All right, let's move along. All right, this was now explained about the Mercury sodium tel. This is the Messenger flyby mission, the second flyby and the third fly, and it shows you that it consists of Mercury sodium tel. Now, the sodium tel, Mercury sodium tel, was known since 1980s, and they knew about it, and with the basically of the Messenger's flyby, they're able to, with the filter, they're able to capture the sodium tel. Now, if you look carefully, you can see the shadow here from the sun. The sun is shining on the left side, and it's caused by solar winds, and it pushes all the sodium molecules away from the sun. But I have here, this is the close-up of the sodium atmosphere, Mercury, and this is the actual diameter, the blue circle here, and this is the tail that's moving away to the right, and the sun is shining, the solar wind is shining from the left, and as you can see the shadow of Mercury against the sodium molecule. The next one is, I hopefully can show you the short animation. You can see as Mercury going around the sun. Here we go. And as Mercury gets close to the sun, the sodium tail grows, and when it's further away, it gets smaller. And as it's going around, you can see the variation. It shows you that again, and you can see it get bigger, and as it moves away from the sun, it gets dimmer. As it gets closer, it grows. This image was taken from the Messenger's flyby. So this is explained to you that it depends on where part of the orbit is near perihelion, whether it's the closer point to the sun, the sodium tail is a lot longer because of the intense radiation from the sun, and when it's the furthest away, it's smaller. Okay. All right, this is the spectrum. Now the sodium had a spectrum of 590-degree nanometers. And this is, as a matter of fact, the two absorption lines here. This is these same for sodium spectrum of the sun. So even the sun has the sodium too, but mainly this is a spectrum of 590 nanometers wavelength. Yes. This is the diagram of all the aspect of the sodium molecules around here. And of course, mercury here, and they have the core here, the mantle, and the crust there. And also within the atmosphere, no, mercury doesn't have any atmosphere like we know it, but they have an exosphere, which contain molecules, sodium molecule, and a combination of other gases too. Like if you look here and you see the atmosphere of mercury composition, it consists of oxygen, sodium, hydrogen, helium, potassium, and others here. Of course, we see the sodium here, which is considered more percentage-wise than any other type of gas. If you look here, and from the solar wind, from the left side of the screen, you can see the sodium molecules pushed it away from the solar winds. Yeah, so it's planetary ions, and also, so really, it was discovered by the messenger spacecraft, able to detect all this different type of gases that mercury. Don't forget, mercury doesn't have atmosphere like we have. But it was detected by a filter-wise spacecraft, messenger spacecraft. Mariner 10, which flew by Mercury 3 times back in 1974 and 75, didn't have any kind of instrument to detect the sodium molecules. And also, during the transit of Mercury, I think one of the project is determine whether or not if the sodium molecule can pick up around Mercury here. Now, if you look carefully, this is on the surface of the sun during the transit. You see all the granulations and all. But if you look carefully around the limb here, it might show some kind of like a blur lines of all around the limb. They believe it might be the sodium part of the atmosphere. Yeah, they're not really sure. It could be, maybe it could be artifact or something like that, but they're not very sure. Yeah. So more work needs to be done during the net transits of Mercury, or whether or not they get able to detect the sodium atmosphere here. This is the same way to find out, if any exoplanet transcends their stars, to see whether or not they have the atmosphere and detected the absorption. So this is very similar way whether if the sodium atmosphere can pick up during the transit of Mercury. Even the moon. Yes, even the moon. The moon extended sodium atmosphere consists of sodium molecules around it. Most planetary systems have some kind of sodium atmosphere around it. Even the Jupiter moon's Io consists of sodium molecule. It puts it away, you can see. But from the moon, where we see the moon, we cannot able to detect firmly, because we look at the moon directly, and there's a sodium tail from the moon, it's behind the moon, and it's very hard to see. But when it's the first quarter or last quarter, we see the moon 90-degree angle. And if you have a proper equipment or some kind of filter or something like that, I'm not really sure it can be detected. But the Earth and Moon system are much further away than Mercury. Mercury has a very intense radiation on it that pushes all the sodium molecule into space. But let me explain something here. We all know the Earth has 5 layers of atmosphere. They have the troposphere, they have stratosphere, they have mesosphere, have thermosphere, and exosphere. Okay, and the troposphere it's the atmosphere which we live in. Okay, then you have the stratosphere, which is most of the high altitude plane clouds. They are within this layer. And then you have further up, they have a mesosphere. This is where most of the meteor burns up or any aurora, something like that. And then you have the thermosphere, which is most of the low orbit satellites we fly here. And then the Earth has the exosphere, which is most of the astronauts able to walk in space at that time with space shuttles, stuff like that. So it's a little bit above the low orbit layer. The exosphere is it consists with all the very faint sodium atmosphere. It consists of all the molecules on the surface of Mercury. This molecule bouncing around, and it's very, very far apart. I mean, it bounces around during the very intense heat from the sun, and from the distance you can able to see like a cloud version. And during the solar wind, it pushes all the sodium molecules away from Mercury towards space. This is quite amazing because this is something new, and this opened up the chapter of imaging Mercury with the sodium filter. Now, the sodium filter, it's not hard to get. I mean, it's some companies sells this, like a Thorn Labs sells it. They run for maybe $125 to $155 to say, and they have an 1.25" filter cell, which can able to attach the adapter of the camera lens and put on the telephoto lens, maybe 100 millimeters, and you don't need a telescope for it. A simple camera with a telephoto lens and a filter on a tripod, and you take time exposure, maybe 5-10 seconds or 15 seconds. I never done that. So hopefully in the near future, if I get the sodium filter, maybe I'm able to do that. But you gotta make sure that Mercury has to be in a fine position. Gotta be favorable position, high above the atmosphere, high above the horizon as much as possible. At the same time, it's getting lower, and you want the darkest sky as possible before it sets. So you gotta capture the right moment. So anyway, even Edmond Optics, they have a sodium filter, and yeah, this is really it opens up the new chapter, imaging Venus and I mean Mercury. That's probably about it. Now Mercury is famous for not a comet list. So that's it, folks.
Thank you very much, Frank.
Actually, Frank.
Yes.
Can you pull up your presentation again real quick?
Oh, yes.
And go to the movie that was showing the changes as the
Okay,
change in
yes.
brightness as it was going around the orbit. Because I think one of the things that's really important to know about this tail is that these are neutral sodium atoms, so they're preferentially scattering light. That's basically where the solar Fraunhofer, the D lines.
Right, yeah.
And so most of the time, it's scattering light from a part of the solar spectrum that isn't very bright.
Okay, yeah.
But there are certain points in its orbit, and I think it's roughly 16 days before and after perihelion, when the Fraunhofer lines
right?
get Doppler shifted out of where the sodium's actually scattering. And that's why you see it brighten, not at perihelion, but 16 days before and then after perihelion.
I'm not really sure that very accurately, but yeah, this is when it gets smaller, then it gets larger, then, well, I don't know if this is very accurate. See, this,
I think what you're seeing there is
yeah.
you're seeing the
Yeah.
change in the Doppler shift. When
Right,
it's at
yes.
aphelion and perihelion, the sodium atoms are only scattering the Fraunhofer lines, which are, as anyone who's done solar spectroscopy, that's
Yeah.
basically little light coming there.
Yeah, that's a good catch, yeah. Yeah.
So there are times during an apparition when this tail is significantly brighter than other times.
You're right. Yeah, exactly. Yes. Yeah. You know that it's very, when it's reaching a further point, you can see the smaller thing. At the larger here, then another point here, it's large right here. See here, and now when it's the closest. That's interesting.
Yep. And we see the same process with actual comets. If you remember back NEOWISE 2 years ago, especially for the first few weeks after perihelion, it was extremely yellow. And that was the sodium you were seeing, reflecting, scattering the yellow light.
Yes.
So basically any body that gets within, say, half an AU of the sun starts showing this sodium scattering.
Right, yeah, okay. Yeah, that's a good thought, yes, yeah. You can see it's yellowish, but I don't know that color from the twilight, morning twilight. This is much darker. And I use the light pollution filter, and you can see that the skybound background is a lot darker. So I live in a light polluted area. So you pick up, some of the sodium gas, the gas.
Yep.
Yeah, okay. Yeah, that's a good thought. Yeah. All right. Yeah. Hopefully next spring, usually in the spring, in favor even apposition, a lot of people around and able to catch mercury. And so hopefully there will be more imaging, and I will do the write-up about the sodium count in the near future.
Okay. Thank you, Frank.
Thank you, Frank.
You're welcome.
At this time, we're going to move along for our final speaker of the afternoon, our final regular speaker of the afternoon, Julius Benton. For those who were not with us yesterday, Julius is a retired aerospace executive. He lives in Savannah, Georgia, along the Atlantic coast, and he had been with General Dynamics before retiring. And he has also been, he also taught at a local college in the Savannah area. Let's see, he retired in 2014. Julius joined the ALPO in 1967, and he has been coordinator of the ALPO Saturn section and the Venus section continuously since 1971. He has also been an ALPO board member for at least 2 decades, and he has served several terms as an ALPO executive director, which is a 2-year stint each time. The title of Julius's presentation right now will be Observing Venus with the ALPO. So Julius, take it away.
Okay, great. Thanks everyone for listening. Go ahead with the next slide, please. Okay, the value of amateur planetary observations. I should mention that the amateurs have the complete freedom whenever desired to observe for extended periods of time. Standardized systematic observations provide long-term continuous records for further study by professionals. Earth-based monitoring by amateurs of changing atmospheric features on Venus can help professionals select targets for high-resolution spacecraft imaging. And skilled observers routinely produce excellent digital images at various wavelengths that are useful to the professional community. The ALPO serves to the original plan for the ALPO was to encourage and coordinate regular systematic observations of investigations of the sun, principal planets, and other members of our solar system. And this was the mission that was established with the founding in 1947 by the late Walter Haas. Okay. Instrumentation for observing Venus. We don't set an inflexible minimum, a 7.5 centimeter or 3-inch refractor. Many of our observers use that size telescope, or stepping up to a little bit more aperture helps improve viewing for both refractors and Newtonians and catadioptrics. Some of our observers are using even larger Newtonians and catadioptrics for imaging Venus and making drawings. Color filters are useful for improving transmission and looking at the planet or imaging the planet in various wavelengths. Low transmission filters improve contrast while limiting the effects of irradiation because Venus is so bright. Blue filters, violet filters are usually used commonly for visual observing Venus. And of course, variable density polarizers improve visibility of faint markings on Venus by reducing glare because a lot of the markings that are in the clouds of Venus are very elusive. For achromatic refractors, a fringe filter helps suppress the secondary spectrum effects. And the astronomical almanac or similar printed or electronic ephemerides are also useful. The digital imaging imager, of course, is useful for imaging, and the PC for processing the images with a PC or with a laptop. Okay, next slide. Keys to meaningful results: start observing each apparition when Venus first becomes well placed for observing, and continue watching until the conjunction with the sun occurs. Use ALPO observing forms to make visual drawings and record reported data. Submit digital images and drawings regularly to the ALPO Venus section. That would be direct to me. My address is also listed in the ALPO website and also in the journal. The high albedo of Venus causes excessive glare against a dark background sky, so low contrast atmospheric features are elusive and sometimes difficult to detect visually. Utilize color filters and variable density polarizers, as I mentioned earlier, to enhance contrast and reduce the radiation and glare. Because atmospheric features on Venus are so elusive, simultaneous observations are very important. Observing Venus at the same time and on the same date as much as possible to observe Venus, and also observing Venus in twilight or daylight hours whenever possible is very helpful because most of the glare associated with the planet is minimized. And when Venus is higher in the sky, atmospheric effects causing poor seeing conditions is reduced, and contrast conditions improve when Venus is seen against a light background sky. Next. Our observing program: visual numerical relative intensity estimates are perceived atmospheric features. Disk drawings of atmospheric phenomena seen or suspected on Venus. Digital imaging at visual, ultraviolet, and infrared wavelengths. Monitoring the visibility of cusp caps, cusp bands, and cusp extensions, and determining the extent and visibility of the bright limb band. Systematic patrol of the dark hemisphere of Venus for the elusive ashen light, and to determine the terminator geometry, monitoring any irregularities along the terminator. Try to detect the Schroeder's effect, which is a difference between the predicted and observed date of dichotomy, half phase, and routine simultaneous observations, as I alluded to previously. Using visual and digital imaging methods is very helpful. Active participation in the ongoing professional, amateur, pro-am work is ongoing right now. The Venus Express mission, which ran from 2006 to 2015, and the current Akatsuki mission, the JAXA program run by the Japanese, is a very, very active program and very, very heavily underway right now. We continue to support that program with submitting images, and they have solicited those images from us for further study. Next. This is a sample Venus observing form, which of course is quite easy to use. Observers can use this at the telescope, and also there's room on the form to record various atmospheric phenomena and the statistics that are associated with the Venus when looking at the planet visually, and also when imaging Venus. These forms are basically available on the website, and I can send them to you. Anyone who would like this set of the forms, I can send by email as well as an attachment. Okay. The elusive atmospheric features of Venus. What do we see? The analysis of visual observations for many years suggests high, rough categories for the atmospheric features on Venus. Banded dusky markings, parallel dusky streaks along the illuminated disk of the planet, perpendicular to the line of the cusps. Radial dusky markings, the curious spoke pattern, the Y pattern that we refer to in a lot of literature. When you look at UV drawing or UV images, you can see this pattern as well. I'll show you some images in a few minutes. Irregular dusky markings have no real form or really streaks on the in the atmosphere of Venus with no specific orientation, and amorphous dusky markings which really have no form, definite shape, or pattern. And bright spots are regions exclusive of the cusps, areas that appear much brighter than the surrounding illuminated disk. The contrast of dusky markings on Venus is usually wavelength dependent. Contrast drops off rapidly at 380 nanometers at the lower limit of the average human eye, because you're getting into the UV region, and observers have varying wavelength and contrast sensitivity thresholds. And that's discussed in my monograph about Venus observing visually. Contrast conditions are often improved, just as I mentioned earlier, when you observe Venus against a light background sky. Venus is so bright that you can sometimes find it quite easily in the sky, in the daylight sky, if you know where to look. This is the latest information on the current western morning apparition of Venus. The planet will reach superior conjunction on October the 22nd. The apparition started out in January and will continue through until the late fall. It's an inferior planet that exhibits phases like the moon, of course, attaining a maximum elongation from the sun of about 47 degrees during any apparition. The current 22 Venus western morning apparition, the following circumstances exist. Venus appears in the eastern sky before sunrise west of the sun's position. Progression is from inferior conjunction to greatest elongation west. Superior conjunction, angular diameter decreases slowly from the earlier 63.3 arc seconds to 9.8 arc seconds, which will occur in October. And observers are witnessing waxing phases from 0 degrees illuminated through dichotomy, again, half phase, and 100% illuminated as the apparition progresses. It's best viewed before sunrise in a twilight or brightening sky for better contrast, as I noted earlier. Okay. Current, past and present amateur professional programs. The Venus VEX mission, which occurred from 2006 and 2015. Observers regularly submitted digital images at UV and IR wavelengths from May 2006 to the end of the mission in late 2015. And although the actual mission is concluded, data analysis is continuing. We continue corresponding with the program director of the VEX mission. The current PROAM program is the Akatsuki Venus Climate Orbiter, which began in April of 2016 and is still underway. And we're continuing to send observations and share those with the professional community. And there is a website to coordinate, to contact to coordinate participating in the program. But we send observations anyway to the Akatsuki team to fill in some of the relevant gaps in the mission's data set. Images taken with multi-wavelength filters are of significant value to the mission, and the ALPO Venus section coordinates sharing of images with the data to the Akatsuki team. All right, a PROAM alert from the Akatsuki team. The newly discovered cloud discontinuity, referred to as the CD, has been occurring in the mid-cloud levels on Venus ever since 1983. The phenomenon is a long-lived disruption within the mid-level cloud layer of Venus at between 48 to 55 kilometers above the surface of the planet, with a westward rotation of approximately 5 days. The higher altitude clouds circulate the Venus in the super rotation at approximately 4 days. The massive structure cuts across the planet's equatorial region at approximately 8,000 kilometers from end to end. This image that appears on this page shows an illustration of what the CD looks like, and it's been reportedly by amateur astronomers using 742 nanometers IR filters through 1 meter filter as well. Visually, the cloud discontinuity is hidden underneath the planet's upper cloud layer, so it's not easy to spot visually. I do not have any visual observations of anyone indicating that the cloud discontinuity is visible. It's mostly imaged in the infrared wavelength. Again, the upper clouds of Venus at 65 to 70 kilometers level exhibit, again, the 4-day super rotation. And this mid-level cloud that we're talking about is about a 5-day period. All right. You'll see labeled on, go back 1 second. You'll see labeled on that dot on that image, arrows pointing to the discontinuity near the limb, near the limb of Venus. Okay. Next. So here's some reliable Venus, recent ALPO Venus observations this year. This is an image that was taken in the infrared during the early part of the apparition in February. These images show the thermal emission from the surface of Venus in the near IR at 1,000 nanometers, penetrating the dense atmosphere. Subtle markings in the images are not atmospheric features. They are warm surface areas emitting in the 1,000 nanometer region in that IR window. And more Venus observations observers should continue to, or should attempt to, image the planet during future apparitions at or near inferior conjunction. This started back years ago when people were sending in these back as far as 2003. Next. Here are some representative drawings and images of Venus showing some of the features I mentioned earlier. As you go from left to right, you can see banded dusky markings. And also these images are taken at visual wavelengths. Some are taken in the IR and some are taken in the UV. The middle image on the top row is taken in the UV, and the one on the far right is taken in the UV as well. Shows the Y cloud feature that I mentioned earlier. As you go across the images at the bottom of the page, you'll see that that same Y-shaped feature it's a Kelvin gravity wave that causes this appearance. And on the far right is another images of the discontinuity that I mentioned earlier. We continue to solicit these images. We're getting images daily. I've gotten a lot of images recently in the IR showing this feature. Some of the images are taken in the IR, in the UV to make comparisons as well. We've got images coming in from Greg Shanos down in Florida, guys in Portugal, Clyde Foster in South Africa, and a number of observers worldwide. Next. This is a drawing by an observer in Germany, Detlef Nietzsche. He's been a regular drawer, a sketcher of Venus over the years, and he has suspected the presence in this set of observations here of the appearance of the dark side of Venus being illuminated. The Ashen light goes back quite some time ago. It was goes back in time to when it was first noted 400 years ago. It says it first appeared in 1643. Some say that due to CO2 in the atmosphere of Venus being split by UV radiation emitting a greenish glow may be some of the causes for this. Others contributed to lightning storms in the atmosphere of the planet. Nothing like the lightning storms we have on Earth, more cloud to cloud type stuff. And still others, it's merely believe it's merely an illusion. So we need to get more observations, simultaneous observations of this phenomenon. It's been one that's been hanging around for a long time. We've solicited the possibility of getting people to make images of it, if that's a very possible situation. That's why multi-wavelength imaging of Venus to try to capture this would be very helpful. Okay, I mentioned a monograph some time ago. This is a guide for visual observations of Venus. It's available on our website. I can send it to anyone who would like to have it. It's in PDF format. There's no cost for this, and I'd be happy to send it to anyone who would like to have it. My email address is available in the journal, as well as I think Tim can make that available to anyone. I think my email address is listed on the opening slide of my presentation as well. And so I encourage anyone who would like to follow Venus. It's a very elusive, it's a difficult planet to observe, to see features on the surface, in the atmosphere. So keep watching and send your observations. We need as many as we can to try to get confirmation of features seen in Venus's atmosphere. Great. Thank you so much for participating.
Thank you, Julius. I would like to say that, Julius and the Saturn section, the Jupiter section, and the Venus section literally get hundreds of images because they're easy planets to image. I'd like to see, and I'm sure the reporters or the coordinators would like to see a lot more images of their planets. That would be Uranus, Neptune, and Mercury, and Mars. Mars gets a lot of input as well. So those of you out there that can do imaging, you know, take a shot at Mercury and Uranus and Neptune and help out those sections.
Yeah, the thing, Ken, is that right now I'm inundated with images and drawings. I've never turned any away, and I would look very much forward to having more and more, because I'm keeping up with them as much as I can from day to day. And we've got observers worldwide. We've got them in Italy, Japan, South Africa, Germany, Australia, and of course, US observers as well participating in our programs. Very welcome.
Okay. Tim?
All right. Well, this closes out the speaker section of our two-day conference. I want to thank everybody for participating. I really want to thank all the presenters. You all did an excellent job. Very good. That was a lot of fun. Here's the agenda for this evening, starting at 23 hours UT or 7 o'clock p.m. Eastern time, 4 o'clock p.m. on the West Coast. Surprise, Carl, you're going to do closing remarks. I don't do that yet, but I'm sure you'll fill up 10 minutes. Followed by that, we're going to do the Walter Haas Observers Award, and then the Mike Reynolds Award, and then the keynote address by Chuck Wood. And then following that, yes, you have to wait through all that to get door prizes. So I have taken everybody's email address that registered, put them in a little bowl, and this is what we're going to be drawing from. Hopefully, I tried to edit out the people that do not live in the United States. So, because
Tim,
postage,
just a quick question: will this be a separate?
Yes,
Zoom link?
It'll be a separate Zoom link. I'll send out 10 minutes after this meeting's over.
Perfect. Thank you.
So,
Thanks,
no worries.
everyone.
Yeah,
This has been great. This has been a great conference. I've enjoyed being here.
Thank you.
This has been fun. All right.
Yeah, I want to say bye to everybody. I won't see you till next time.
Okay.
You won't be here tonight, Phil?
I might see it on YouTube. I don't know. I got to go to a meeting.
Okay.
So I hate to do it, but I'm the secretary. I got to take the notes and all that.
More door prize chances for us.
Yeah.
Yeah.
I don't need any door prizes.
No, his door prize is still in there. So you don't have to be present.
We have.
I really don't care about door prizes.
Oh, okay. I'll put my name in twice.
No, all right. Works for me. Well, anyways,